What if the Big Bang wasn't the start of everything, but rather the most recent episode in a long-running cosmic drama? We thought we knew the story, but new information, better telescopes, and bold ideas are changing it. It's possible that the universe didn't just appear out of thin air. It could be the child of a black hole falling, the echo of an older universe, or the expansion of space itself after a huge contraction. Scientists are finally putting together what might have happened in the mysterious moments before everything we see came into being. They are finding evidence of things like quantum jitters frozen in time and hidden gravitational waves. So what exactly happened before the Big Bang? Limits of the standard Big Bang model. People have thought about the Big Bang as the most likely way for the world to have started for many years. This model has done a great job of showing how the universe changed over time from a hot, dense state to the web of galaxies we see today. That being said, there is a huge problem at the very beginning that makes the whole plan unstable. You reach a wall when you try to use the equations of general relativity to go back in time and shrink the world to earlier and earlier times. The math stops making sense around 13.8 billion years ago. There are no limits on how dense things can get or how high temps can go, and space-time curves into something we can't explain. It's not just a computer glitch. This shows that the standard Big Bang model does not really explain how the world began. The singularity is the name for this strange place where things begin. But don't picture it as a tiny dot in space that's about to blow up. The singularity is not a real thing. It's what happens when our models break down in very special situations. Einstein's general theory of relativity is the best way to explain gravity and the shape of space-time. It works great for planets, stars, and galaxies. But it doesn't work at the Planck scale, around 10 to the power of minus 35 meters, an unimaginably tiny distance. This is where quantum effects dominate. In mathematical terms, the singularity is like a big red flashing sign that screams, "Your theory doesn't work here." And that's a big deal because the singularity is where everything we want to know about the universe's birth should be hiding. What really happened in those first fractions of a second? Did the universe spring from nothing? Or was there a phase before the Big Bang? Did space-time itself begin? Or was it transformed from something else? The standard Big Bang model can't answer these questions because it simply stops at the singularity. In a way, it's not so much a theory of the universe's beginning as it is a theory of its evolution after the first measurable moment. The problem begins when you trace general relativity all the way back to the Planck epoch, the earliest known moment after the Big Bang, just about 10 to the power of minus 43 seconds after it all began. That's the smallest slice of time we can currently describe. Before this epoch, densities were so high and gravitational effects so extreme that quantum mechanics and gravity were tangled together in ways we still don't understand. General relativity treats space-time as smooth and continuous, but quantum mechanics suggests that, at such small scales, space-time might be grainy or made up of discrete chunks. Trying to apply general relativity in this regime gives nonsensical answers, like infinite density and infinite curvature, things that don't exist in the real universe. People often get the singularity wrong by viewing it as a kind of explosion point in space. In the usual sense, the Big Bang wasn't a blast. It wasn't something that happened in space. It was space itself getting bigger. There was no middle or edge. The room between points grew bigger, and as far as we can tell, this growth happened everywhere at the same time. The singularity is not a tiny spot in space where all matter was squished together. It is a state in which our knowledge of physics falls apart. This breakdown of general relativity at the singularity is one of the strongest clues that we need a new theory, one that combines the smooth geometry of relativity with the quantum uncertainty of the microscopic world. Scientists call this missing framework quantum gravity. Without it, we can't properly describe the Planck epoch or whatever came before it. Several candidates are being explored: string theory, loop quantum gravity, and other quantum cosmology models. But none are confirmed. Until one of these theories succeeds, the singularity will remain an impenetrable wall. Even without a full theory of quantum gravity, there are hints that the singularity might not be the absolute beginning after all. Many cosmologists believe that the infinities predicted by general relativity are artifacts of pushing the math too far, not actual features of the universe. In other words, the universe may never have reached a true singularity. Instead, it might have gone through a phase where classical physics simply doesn't apply, transitioning smoothly into the hot, dense state we call the Big Bang. Some models suggest that before the familiar expansion phase, the universe could have existed in a different form, perhaps slowly contracting or sitting in a stable quantum state. The so-called Big Bounce theories, for example, propose that our universe could have been born from the collapse of a previous one, rebounding instead of reaching an actual singularity. Loop quantum cosmology supports this by showing how quantum geometry could prevent space-time from ever shrinking to infinite density. In this view, the singularity disappears, replaced by a bounce that marks the transition from an older phase to our current expanding universe. There are still questions about what started the rapid growth of space fractions of a second after the Big Bang, even in the popular inflation theory. It's not clear if it started at the singularity or earlier. Some models of inflation say it might last forever in some places. This means that the Big Bang might just be the first in a long series of cosmic increases. Cosmic inflation basics. In the first unimaginable fraction of a second after the Big Bang, the universe did something extraordinary, something so strange it still feels almost impossible to comprehend. In less than 10 to the power of minus 32 seconds, space itself expanded faster than the speed of light. But these weren't galaxies flying apart like shrapnel from an explosion. It was the very fabric of space stretching, dragging everything along with it in a burst of rapid growth that we now call cosmic inflation. Without this brief but dramatic event, the universe we see today, with its galaxies, stars, planets, and even us, might never have formed. It was suggested that cosmic inflation could explain a number of problems that the standard Big Bang model couldn't. Scientists noticed something strange when they looked closely at the universe. The universe seems very uniform no matter where we look. There are very small changes in the temperature of the cosmic microwave background, which is the oldest light in the universe. The temperature changes are almost the same in all directions. The basic Big Bang model says that faraway parts of the universe should never have come into contact with each other, so this amount of smoothness is strange. So far away from each other that even at light speed, there hasn't been time for information to get between them. How did it happen that these places got pretty much the same temperature? To solve this game, you need to find the horizon. Inflation provides an elegant solution. Before inflation, the universe was much smaller, and all of its regions were close enough to talk to each other, exchanging heat and energy until they reached the same temperature. Then, in a split second, inflation stretched this tiny uniform region into something vast. Regions that are now billions of light years apart were once neighbors. The uniformity we see today is simply a stretched out snapshot of that early thermal equilibrium. Another puzzle was solved by inflation, the flatness problem. The universe is very close to being flat in terms of its shape, as seen through observations. The sides of a triangle drawn across billions of light years would add up to 180 degrees, just like they would on a piece of paper. But general relativity says that the early universe could have been curved in any way. It would have had to have been fine-tuned to an absurd degree for it to look this flat today, unless something naturally smoothed it. That's exactly what inflation does. Space became flat on a large scale because of rapid growth, which smoothed out any bumps or wrinkles. It's kind of like zooming in on a small part of a curved balloon. But inflation didn't just solve problems. It created the seeds of everything we see around us. During that rapid expansion, tiny quantum fluctuations, random jitters in energy at microscopic scales, were stretched to cosmic sizes. These fluctuations became slight variations in density. Some regions ended up just a little denser than others. Over billions of years, gravity amplified those differences, pulling matter into clumps, forming galaxies, stars, and eventually planets. Without inflation, the universe might have been too smooth for any structure to form at all. So how exactly did this inflation happen? The theory suggests that in the earliest moment of the universe, space was filled with a peculiar energy field. often called the inflation field. Think of it like a ball balanced at the top of a hill. While the ball stayed at the top, its energy drove rapid expansion, pushing space to grow exponentially. Eventually, the ball rolled down to a lower energy state, releasing its stored energy. This release heated the universe, filling it with particles and radiation, the hot, dense state we traditionally associate with the Big Bang. In this sense, the Big Bang as most people imagine it, the burst of heat and light, actually happened after inflation ended. The timing of this event is almost beyond imagination. Inflation likely lasted from about 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the universe was born. In that tiny fraction of a second, the universe expanded by a factor of at least 10 to the power of 26, growing from smaller than a subatomic particle to something far larger than our entire observable universe today. And then it stopped just as suddenly, leaving behind the uniform, flat but slightly lumpy cosmos we inherited. The most important question is, what caused it? Why was there an inflation field to begin with, and why did it stop growing at that point? There are even ideas that inflation might never really stop. This idea, called eternal inflation, says that inflation may have stopped in some places, like ours, but it's still going on in other places, making new pocket universes that might have different physics. This directly leads to the idea of the multiverse, which is a natural result of the math behind inflation. Scientists are working to confirm inflation by looking for its fingerprints in the cosmic microwave background. One of the most important clues would be primordial gravitational waves, tiny ripples in space-time caused by the rapid stretching of the universe. These waves would leave a distinct pattern, called B-mode polarization, in the CMB's light. Detecting this signal would be like hearing the faint echo of inflation from 13.8 billion years ago. So far, no conclusive detection has been made, but experiments like BICEP, the South Pole Telescope, and upcoming missions such as LIGHTBIRD and SPHEREX are hunting for it. Inflation as the first phase. It is because of inflation that we can understand many things about the early universe, such as why it is flat and uniform, and how tiny quantum ripples turned into galaxies. But the questions get stranger as you learn more about the idea, because what causes inflation is what really puzzles people, not how it works. What caused that incredibly fast growth in the first place? What was there right before it started? Inflation theory treats the early universe as if it were dominated by a mysterious energy field, nicknamed the inflaton. This field was in a high-energy state, like a ball balanced precariously at the top of a hill. While it stayed in that state, it pumped energy into space, making it expand exponentially. Then, almost instantly, the field rolled down to a lower energy state, releasing its stored energy and filling the universe with heat and particles. That's when the hot Big Bang, the event we usually imagine as the universe's beginning, truly started. But what put the inflaton there in the first place? And why did it roll when it did? According to one theory, inflation didn't need a cause because it was built into the nature of space-time itself. Some models say that inflation will happen naturally if space-time ever hits a certain level of high energy. There's no need for a spark. That's just how energy acts in those situations. But this answer makes the puzzle even less clear. So why did the world have that much power to begin with? Did it turn on all of a sudden? Or had it been sitting there doing nothing for a while? The standard Big Bang model assumes that time itself began at the moment of expansion, making the question meaningless. But many physicists aren't satisfied with that answer, because inflation itself behaves as though something came before it. If the inflaton field existed, it had to exist somewhere. Did the universe have a pre-inflation phase? Was there a quiet, stable state before everything erupted into motion? Some hypotheses, such as the emergent universe paradigm, support this. The universe may not have begun with a singularity or a burst of growth. Instead, it may have been in a calm, almost timeless state for an infinite amount of time, like a cosmic egg. During this situation, inflation wasn't the very start. It was more like water suddenly turning into steam. The universe might have been in a safe state, waiting for the right quantum fluctuation to happen so that it grew very quickly. Other models go even further, proposing that the universe didn't begin at all, but instead bounced from a previous state. Loop quantum cosmology, for example, replaces the singularity with a bounce. According to this theory, a contracting universe shrank to a minimum size before quantum effects caused it to rebound, expanding into what we now see as the Big Bang. Inflation could have been triggered naturally in that bounce, as the energy density spiked during the rebound. There's also the chance of a beginning in more than one universe. Models of eternal inflation say that prices will go up again and again over time. In some places, it stops, creating bubble universes. But in other places, it keeps going. It's possible that our universe began inside a much bigger background that was expanding. What caused our bubble to pop could have been nothing more than the normal changes in this bigger place that was expanding. That is, inflation doesn't just happen sometimes. It happens all the time, but not everywhere. But if that's the case, what triggered inflation in the very first place, in the very first bubble? That question is still open. Some theorists argue that inflation may be eternal, both forward and backward in time, stretching infinitely with no first trigger. Others suspect that inflation had a beginning, possibly emerging from a quantum fluctuation in a pre-existing vacuum, or even from the collapse of a previous universe. Loop quantum cosmology, LQC. The usual model of the Big Bang finishes with a singularity, which is a mathematical nightmare where temperatures, densities, and the curvature of space-time all go to infinity. But loop quantum cosmology, LQC, tells a different story, one that doesn't have a singularity at all. The world doesn't have an endless point of nothing. Instead, it bounces back and forth. It gets smaller until it's almost empty. Then it expands again, making a smooth transfer into what we call the Big Bang. There will be no infinities or breaking down of physics. There will only be a new phase of space-time ruled by quantum rules. LQC is built on the foundations of loop quantum gravity, LQG, a theory that attempts to unite general relativity with quantum mechanics. General relativity treats space-time as smooth and continuous, like a perfectly stretched sheet. But LQG says that at the smallest possible scales, the Planck scale, around 10 to the negative 35th meters, space-time isn't smooth at all. It's granular, made of discrete loops, or quanta of geometry, woven together like a microscopic fabric. You can't slice space into infinitely smaller pieces, because at some point you hit its fundamental building blocks. And this changes everything about how gravity behaves under extreme conditions. As the universe contracts toward what would have been a singularity, quantum geometry kicks in. Normally, gravity is always attractive. The more mass you cram into a region, the stronger gravity pulls inward. But at ultra-high densities, LQC predicts that quantum effects create a repulsive force. This isn't just a tweak to gravity, it's a complete reversal. When the density approaches the Planck scale, this repulsive quantum pressure grows strong enough to halt the collapse entirely. Instead of shrinking into a singularity, the universe reaches a minimum volume and bounces back, starting to expand again. This bounce means a lot of things. It makes me think that the Big Bang wasn't really the start of things, but rather a change. A universe could have existed before ours. It might have slowly shrunk until it reached a quantum limit, at which point it grew again. In this shot, time goes on and on across the bounce. Before the hot, dense fireball of early astronomy, there was a before that looked very different. What makes LQC especially appealing is how it solves several long-standing problems. The singularity, with its infinite curvature and density, simply doesn't exist. Instead, the laws of physics remain valid all the way through the bounce. Energy density is capped at a finite maximum, about 0.41 times the Planck density, according to simulations. Space-time never becomes infinitely curved, and the universe never compresses to zero volume. LQC also naturally smooths out some of the same issues inflation was designed to fix. The quantum bounce can, under certain conditions, generate nearly scale-invariant fluctuations, the kind that seeded galaxies and match what we observe in the cosmic microwave background. In some LQC models, inflation still happens after the bounce, but it may be triggered automatically by the rebound itself. That means the universe doesn't need extremely fine-tuned initial conditions to start inflating. It just happens as a consequence of the bounce dynamics. The mathematics behind LQC comes from rewriting general relativity using loops of quantized geometry. Space-time is expressed as networks of finite areas and volumes, not smooth surfaces. As these networks evolve, they change in discrete steps rather than flowing continuously. In a contracting universe, this quantum discreteness resists further compression, creating that repulsive effect at extreme densities. But does LQC leave any fingerprints we can detect today? Possibly. Because the bounce erases the singularity, it might leave behind subtle imprints in the oldest light, the cosmic microwave background. Some LQC models predict small deviations in the temperature and polarization patterns, especially on the largest scales. There might also be distinctive gravitational wave signatures generated during the bounce, different from the ones expected in standard inflation. Detecting such signals would be a huge step toward confirming that a pre-Big Bang phase really existed. The idea of LQC isn't yet complete. One problem is making clear links between its predictions and what has been seen. A lot of its results rely on certain ideas about how the universe worked before the bounce. Was it closing all the time? Was it controlled by matter, radiation, or some other strange field? Due to the fact that different answers lead to slightly different predictions, it is hard to say for sure what we should look for. Loop quantum gravity is where LQC comes from, but LQG hasn't been tested in the real world yet, so its basic structure is still theoretical. Big bounce mechanics in LQC. We thought we knew everything about how the universe began, but the Big Bounce is one of the most surprising things that LQC says happens. LQC says that the universe didn't start in a singularity, which is that point of infinite density where the rules of physics don't apply. Instead, it just bounced back. A previous universe shrunk down to an incredibly small but limited space. It then bounced back, growing into the universe we live in now, thanks to a quantum force that pushes things away. No endless lists. Physics doesn't break down, it's just a continuous loop that is controlled by quantum rules. The mechanics of this bounce come directly from the way LQC modifies general relativity at ultra-high densities. Einstein's equations describe gravity as the curvature of spacetime, and under normal circumstances, gravity is always attractive. As matter clumps together, it pulls more matter inward, making stars, black holes, and galaxies. But general relativity doesn't take into account the grainy quantum structure of spacetime at the Planck scale, about 10 to the power of minus 35 meters. At those scales, the smooth geometry Einstein described no longer applies. In LQC, spacetime is made up of discrete quantized chunks. These chunks are small circles of geometry that can't be split up any further. These loops don't get smaller than their minimum size as the universe gets closer to Planck densities. It's like when you squeeze spacetime too hard, it gets stiff. There is now a new quantum force that acts differently than traditional gravity. When densities are very high, this force stops pulling inward and starts pushing away, stopping further fall. The bounce happens when the energy density reaches a critical value, about 0.41 times the Planck density, according to detailed simulations. At this point, the quantum repulsion dominates, halting the collapse. The universe never reaches zero volume or infinite density. Instead, it slows, stops, and reverses. In less than a Planck second, it transitions from contraction to rapid expansion, naturally leading into conditions similar to those of the Big Bang. What's fascinating is that this bounce doesn't just erase the singularity, it also implies there was a universe before ours. That previous universe went through its own cycle of expansion and contraction, shrinking over vast timescales until it hit the quantum limit and rebounded. In this view, time didn't begin at the Big Bang. Instead, it stretches infinitely in both directions, with countless bounces in an endless cosmic sequence. The way the bounce works also has an effect on the world we see now. QED was already happening in the matter and shape during the contraction phase. When the bounce happened, these changes carried over into the expansion phase, where they might have started the changes in density that would later turn into galaxies. Some LQC models even say that the bounce can cause changes that don't depend on size, acting like inflation, or even taking its place. That is, the web of galaxies, stars, and clusters that make up our universe may have its roots in an earlier universe. How smooth and predictable the bounce is one of the most interesting things about it. In the usual picture of the Big Bang, the singularity is a sharp edge where physics stops working. In LQC, on the other hand, the equations are still correct after the bounce. The world is always changing. If you could watch the whole process, you'd see it shrinking, stopping to its smallest size, and then growing again, as if it were just going the opposite way. Time doesn't have an edge, it just changes. Does this mean every bounce produces a universe like ours? Not necessarily. The conditions on either side of the bounce depend on what the contracting universe contained. Was it dominated by matter, radiation, or some exotic energy field? Different initial conditions can change how smooth or lumpy the post-bounce universe becomes. But one of LQC's strengths is its robustness. Regardless of these details, the singularity never appears, and a bounce always occurs once densities approach the quantum threshold. How can we check this then? In the cosmic microwave background, CMB, the bounce might have left marks that can be seen. Some LQC models say that the power spectrum of changes in temperature will be slightly different, especially at the biggest scales. Gravitational waves from the contraction phase might also have their own fingerprints that are different from those predicted by inflation. Things like these are hard to find, but new missions like SPHERE and more powerful gravitational wave observatories might be able to. Emergent universe models, cosmic egg. The emergent universe model is a very different story from the usual one about the Big Bang. In this situation, the universe didn't start with a violent singularity or a quantum bounce. Instead, it was calm for an infinite amount of time before it grew quickly, like the Big Bang. People often called it a cosmic egg because it sat there in a steady, almost eternal state, waiting for the right conditions to cause it to expand. The universe did not appear out of thin air when that spark went off. It went from being stable to growing, which is how the expanding universe we see today came to be. The main idea behind the emergent universe is that space and time were really there before inflation. The usual Big Bang model says there was a clear beginning, but this model says the universe didn't really start in the usual sense. It has always been there, kind of stuck in a state where it wasn't growing or shrinking, it just existed. This state is typically shown as a universe that is closed, positively curved and perfectly balanced, so that its size stays almost the same forever. There was matter and radiation, but their densities were steady enough that they didn't collapse or expand too quickly. What I like most about this situation is how naturally it gets around the problems of the standard model. There isn't a singularity, an infinite density, or a riddle where something comes from nothing. Not only did the world not appear out of thin air, it was always there, balanced. After that, something changed. The cosmic egg became unstable because of that change, which is often described as a shift in the properties of a scalar field or exotic matter. This caused the universe to enter an inflationary phase. The fast growth started, and then there was the well-known hot Big Bang. The mechanics of this transition depend on the specific version of the emergent universe model. In some versions, a scalar field was trapped in a false vacuum, a stable but temporary energy state. Over time, quantum fluctuations or slow energy decay caused the field to roll to a lower energy state, releasing its stored energy and triggering inflation. In others, exotic matter with unusual properties kept the universe in balance until it slowly decayed, allowing expansion to take over. In both cases, the universe essentially woke up from an eternal slumber. This never-ending state before inflation also answers some questions about the universe. Since the universe has been around forever, areas had a lot of time to trade heat and energy and reach thermal balance. When expansion finally started, the temperature of the whole universe was the same. This was an obvious answer to the horizon problem. In the same way, The problem of flatness is not as bad because the universe had an infinite amount of time to smooth out any curves before inflation happened. It doesn't matter how well the original conditions are set up for inflation to continue working after the emergent phase. It still stretches space and causes changes in density. The egg from space had all the time in the world to get ready. The emergent universe also stays away from the idea of a beginning of time, which is one of the most important ideas in astronomy. Philosophically, it's hard to explain a real beginning, where time itself begins, in terms of science, which is based on cause and effect. Cause and effect would still work if time didn't start. To explain, this model doesn't have a first moment. Instead, it shows a change from one endless phase to another. But can we test this idea? The emergent scenario leaves possible observational signatures, especially in the cosmic microwave background, CMB. Because the universe was static for so long, some models predict specific patterns in the largest scale fluctuations, slightly suppressed temperature variations, or unique imprints from the pre-inflation state. These would be different from the signals expected from a singular beginning or a bounce. Additionally, certain versions of the emergent universe predict lower levels of primordial gravitational waves than standard inflation, which could be a crucial way to distinguish between them. Eperotic Universe and Brain Collision. The Eperotic Universe is one of the most ambitious and exciting ideas other than the normal Big Bang. Instead of a singularity or a quantum bounce, it says that the universe was formed when two huge higher dimensional membranes, or brains, collided in what is called the bulk. This violent crash didn't happen in nothingness. It happened in a world with more dimensions, just like string theory and M theory say it would. When the brains hit each other, they released a huge amount of energy that heated the area and began what we think of as the Big Bang. The word eperotic comes from the Greek term ekperosis, meaning conflagration, an ancient philosophical idea of a periodic cosmic fire. The name fits perfectly, as this model replaces the standard cosmic birth with a catastrophic event that sets the universe ablaze with matter and radiation. But unlike the Big Bang's singular beginning, the eperotic scenario has no true starting point. The brains existed long before the collision, and in some versions of the theory, they have collided many times, creating a cyclic universe with an infinite history of cosmic rebirths. The mechanics of the Eperotic universe are rooted in higher dimensional physics. According to M theory, which unifies different versions of string theory, our familiar three-dimensional universe could be a brain, a three-dimensional surface embedded in a higher dimensional bulk. Imagine two parallel sheets floating in a vast, higher dimensional space. For ages, these brains drifted slowly toward each other. Their approach was smooth and almost imperceptible, but when they finally touched, the impact released colossal energy. That energy transformed into the hot, dense plasma that filled our universe, mimicking the conditions of the traditional Big Bang, but without a singularity. Cosmologists are interested in this model because it fixes some of the problems that inflation was meant to fix, without needing a very fast growth. Space is automatically smoothed out and made flat during the slow contraction phase before the collision in the Eperotic model. Small flaws are smoothed out because the energy density of the brain's motion is higher than any original curvature or anisotropy. It was already uniform and flat in the universe when it crashed, so there was no need for a second inflationary burst. But the Eperotic scenario doesn't just smooth things out. It also explains how the structures we see today could have formed. As the brains approached, tiny quantum fluctuations in their positions translated into variations in energy density after the collision. These ripples became the seeds of galaxies and galaxy clusters, just as inflationary fluctuations did in the standard model. In fact, the Eperotic model predicts nearly scale-invariant fluctuations, very similar to what we observe in the cosmic microwave background, CMB. Some versions even predict distinct signatures, such as a particular pattern of non-Gaussianities, that could help distinguish it from inflation. The thought of a cyclic universe is one of the most interesting things about Eperotic. The branes don't just hit each other once in the circular version. After each hit, they move apart, spread out for billions of years, and then slowly drift back together. Each clash starts a new phase like the Big Bang, making a series of cosmic births that keep happening. There is no need for a beginning of creation. The cycle could go on forever, with each world leaving only faint signs of the ones that came before it. Testing the Eperotic Universe, however, is challenging. Like inflation, it makes predictions about the CMB, but the differences are subtle. For instance, the Eperotic model predicts far weaker primordial gravitational waves than inflation. If upcoming experiments, like LIGHTBIRD or CMBS-4, fail to detect these waves, that would be consistent with an Eperotic origin. Additionally, its unique non-Gaussian signatures, slight deviations from perfect randomness in the CMB fluctuations, could provide evidence. But detecting these patterns requires extremely precise measurements. A lot of questions remain about how the collisions work as well. What does it mean when branes bump into each other? String theory gives us a framework, but we don't have a full mathematical explanation of the effect yet. What decides how far apart the branes move after they hit each other, or how long it takes for them to hit each other again? Some forms of the theory say that dark energy, the mysterious force that is speeding up the expansion of our universe, could control the timing, pulling the branes apart and then letting them drift back together. Cyclic Eperotic Cosmology. If you think about the Eperotic Universe, it's already a big idea, but the Cyclic Eperotic Universe takes it even further. The world has no real beginning or end. Instead, it goes through an endless loop of shrinking, bouncing, growing, and then shrinking again. Each cycle gets rid of the problems that were there in the last one, restarting the universe before it starts over. From this point of view, the Big Bang wasn't a one-of-a-kind event. It was just the most recent beat in a beat that will never end in the universe. The foundation of this model lies in the same brane collision mechanism as the standard Eperotic scenario. According to M-theory, our universe could be a three-dimensional brane floating in a higher dimensional bulk, parallel to another brane. In the cyclic version, these branes don't collide just once. Instead, they move apart after every collision, slowly drifting back together over trillions of years. When they collide again, the impact generates another Big Bang-like burst of heat and radiation, starting a new cycle of expansion. What makes the cyclic Eperotic model particularly compelling is how it naturally solves several long-standing cosmological puzzles. In each cycle, the slow contraction phase before the collision smooths out any curvature or irregularities. Unlike the explosive inflationary phase, which stretches space extremely fast, the Eperotic contraction phase flattens the universe over vast timescales, ironing out any chaos left from the previous cycle. By the time the branes collide, space is already uniform and flat, and when it expands again, it inherits that smoothness. The model also does a great job of avoiding the problem of entropy building, which has been a problem for cyclic theories for a long time. In traditional circular models, entropy builds up with each cycle, making each new cycle longer and bigger than the last. This builds up until there is a heat death. In the Eperotic form, however, there is an important difference. Dark energy speeds up expansion in the last few stages of each cycle, which lowers the entropy. As the branes move farther apart, dark energy stretches space so much that the universe starts over. Only a small, smooth patch stays to start the next cycle. Without breaking the second law of thermodynamics, this process lets the loops happen over and over again. The idea that this model does not start from the cosmos is one of its most remarkable features. There is no single point in time where it all began. The cycles go back in time forever and will keep going forever into the future. Every Big Bang we see is just one in a line. There is no one first event. You wouldn't find a beginning if you went back in time far enough. You would only find more loops. Cyclic Eperotic cosmology also makes testable predictions that differ from standard inflation. For one, it predicts a much lower level of primordial gravitational waves. Inflation generally produces a detectable background of gravitational waves imprinted in the cosmic microwave background, CMB, as B-mode polarization. If future missions fail to detect these waves at the levels inflation predicts, that could be evidence for a cyclic scenario. The model also predicts specific types of non-Gaussianities, slight deviations from perfect randomness in the CMB's density fluctuations, caused by the slow contraction phase. These patterns are subtle, but they're within the reach of upcoming CMB experiments. It's also interesting to see how each cycle changes over time. After the collision, the universe grows and changes in a way that is similar to how our own has. Stars form, galaxies group together, and dark energy finally takes over, speeding up the expansion. Over many trillions of years, black holes disappear, matter gets less dense, and the universe is almost empty. But this state of being empty won't last forever. As the brains slowly move back together, the contraction phase starts up again. This pulls everything closer together until another clash causes the next Big Bang. New Eperotic Cosmology. The first form of Eperotic was brave, but it wasn't perfect. It fixed the problems of flatness and horizons and escaped the singularity, but it had a big problem. It wasn't stable. The slow contraction phase that the universe needs to smooth and flatten out could easily make anisotropies bigger. Anisotropies are small changes in direction that might get bigger out of control instead of going away. That would make the universe less ordered, and it might collapse into a mess of irregularities instead of spreading smoothly again. There is a better theory called the New Eperotic Cosmology that tries to solve these issues with a clever process called the ghost condensate bounce. The ghost condensate is an exotic field that behaves very differently from normal matter or radiation. In typical cosmology, energy conditions, especially the null energy condition, NEC, prevent a smooth transition from contraction to expansion. Violating the NEC is usually associated with physical instabilities, like runaway energy fluctuations or ghost particles with negative kinetic energy, which would make the theory unphysical. But the ghost condensate field is a special case. It can violate the NEC safely, just long enough to allow a bounce, without introducing the catastrophic instabilities that plagued earlier Eperotic models. In the new Eperotic scenario, the universe first goes through a long Eperotic contraction phase, just like in the original model. During this phase, the energy density is dominated by a scalar field with a steep negative potential. This field smooths and flattens the universe, ironing out curvature and anisotropies. But instead of heading directly into a singularity, the ghost condensate field takes over near the end of contraction. Its unusual properties create a repulsive pressure at ultra-high densities, halting the collapse and reversing it into expansion. In other words, it replaces the violent brain collision of the standard Eperotic model with a controlled stable bounce. That it can make almost scale-invariant perturbations, tiny changes in density that are almost exactly the same as those promised by inflation, is one of its biggest successes. It's important to note that these changes are what caused the galaxies and clusters we see today, and they match trends seen in the cosmic microwave background, CMB. The first Eperotic model had trouble making these changes without adding other problems. The ghost condensate process fixes this by letting the scalar fields change in a more controlled way during contraction. Being stable is another benefit. It gets around the problems of anisotropy and chaos by carefully planning the potential and behavior of the ghost condensate field. The phase of contraction stays smooth and steady, and the bounce happens automatically when quantum effects take over. Because of this, it is one of the theoretically most sound models for the early universe that doesn't include inflation. The new model also fits neatly into the bigger picture of cyclic cosmology. It can be embedded in scenarios where the universe undergoes repeated cycles of contraction and expansion, with the ghost condensate bounce acting as the reset mechanism each time. Instead of brane collisions, the cycles are driven entirely by scalar field dynamics within our own 3D universe, making the model less dependent on speculative higher dimensional physics. But can we distinguish this scenario from inflation observationally? That's where things get interesting. The new Eperotic cosmology predicts different signatures in primordial gravitational waves. Unlike inflation, which typically produces a detectable background of long wavelength gravitational waves, Eperotic contraction strongly suppresses them. If future CMB experiments continue to find no evidence of primordial gravitational waves, it could favor eperotic models over inflation. Additionally, the model predicts specific types of non-Gaussianities, subtle patterns in how density fluctuations deviate from perfect randomness. These patterns could eventually be detected by high-precision surveys of the CMB and large-scale structure. There are still questions about the plan, even though it has some good points. One problem is figuring out what the ghost condensate field is really made of. It's just a theory that hasn't been proven in the real world yet. Scientists are also trying to figure out how the field smoothly changes from contracting to expanding, and if its features can come from a more basic theory like loop quantum gravity or string theory. Conformal Cyclic Cosmology, CCC. Some of the bravest and most creative ideas for explaining what happened before the Big Bang are found in Conformal Cyclic Cosmology, CCC. Roger Penrose, a physicist who won the Nobel Prize, came up with the concept of cosmic continuity, CEC. It says that our universe is just one in an endless chain of eons, or whole cosmic lifetimes, where each one ends and smoothly changes into the next. There is no point of no return and no abrupt starting or end. Conformal geometry is a very cool mathematical trick that makes the end of one world slowly fade into the beginning of a new one. At the heart of CCC is the idea that the distant future of a universe and the very beginning of the next are physically similar when viewed in a certain way. In the far future, trillions of years from now, our universe will become almost empty. Stars will burn out, black holes will evaporate, and only massless particles like photons will remain. Without mass, the concept of time as we know it becomes meaningless. The universe essentially stops changing in any measurable way. In this final, cold state, distances and time intervals lose significance, and space-time can be reshaped or conformally rescaled. Conformal geometry is the mathematical key. It ignores absolute scales of size and focuses only on shapes and angles. If you strip away all sense of scale, the infinitely stretched cold end of one universe can be transformed into a hot, dense beginning of the next. In other words, what we see as the Big Bang in our eon might just be the conformally rescaled, smoothed-out future of a previous universe. This process repeats endlessly, with each eon expanding, fading, and giving way to the next in a seamless cycle. CEC says that information from one eon might last into the next. This is one of their most unusual statements. Penrose specifically says that the disappearance of giant black holes near the end of a universe might leave behind small marks in the cosmic microwave background CMB. Over unbelievably long periods of time, black holes give off Hawking radiation, which is made up of their mass. Their last bursts of energy may be sent into the next part of the Big Bang as faint signals. Penrose and his collaborators have even claimed tentative evidence for this idea. They searched the CMB for unusual features, specifically concentric low-variance circles, sometimes called Hawking points. These circles would be the leftover signatures of energetic events, like black hole evaporation, from the previous eon. While some statistical analyses have claimed to find these patterns, others dispute the results, arguing that the signals aren't significant enough to confirm 300. For now, the evidence remains controversial. What makes CCC so compelling is how it eliminates the singularity problem entirely. There's no need for a quantum bounce, no breakdown of general relativity, and no abrupt starting point for time. The universe simply evolves continuously from one eon to the next, obeying the same underlying physical laws. It also doesn't require inflation to explain the uniformity of the cosmos, because the previous eon's final state is already smooth and homogeneous. The next universe inherits that flatness and uniformity naturally. How massless and heavy particles act at the change between eons is one of the most important questions. All mass has to go away at some point for the conformal rescaling to work. Normal matter will naturally go through this over very long periods of time, but no one fully understands how all traces of mass are lost before the change. Also, CCC doesn't easily explain the structure of the quantum fluctuations that started galaxies, but Penrose says that random thermal effects in the past eon could explain them. 3C's predicted CMB rings. The cosmic microwave background, CMB, which is the oldest light in the universe, may hold clues to a world that existed before ours. This is one of the most outlandish claims of conformal cyclic cosmology, CCC. Roger Penrose says that the dying stages of the last eon should have left behind this old radiation that can be picked up. These marks aren't made by chance. In the CMB sky, the CCC forecasts clear patterns, low variance rings that are spread out in a circle, which are sometimes called Hawking points. It would be the first straight proof that our universe was born from the death of another one, if these rings are real. Here's how these rings are supposed to form. In the far future of an eon, black holes are among the last surviving cosmic structures. Over unimaginable timescales, far longer than the age of our current universe, even supermassive black holes will eventually evaporate via Hawking radiation, releasing their mass as bursts of energy. In 300, when the old universe fades into its conformally smoothed-out state, these final bursts aren't lost. Instead, they carry through into the next eon. When our universe began, those ancient energy releases manifested as slightly hotter, circular regions in the CMB. Because many black holes evaporated in the previous eon, their final signals should overlap, producing concentric rings with lower temperature variance than surrounding regions. The reasoning behind the low variance is subtle. These circles are not just random hot or cold spots. They are regions where temperature fluctuations are unusually smooth, as if something wiped away the normal random noise. The overlapping Hawking radiation from black holes in the previous eon would have acted like a gentle iron, flattening the usual CMB patterns in circular zones. Detecting these low variance circles is therefore a unique signature of CCC, something inflationary models don't predict. Penrose and his collaborators first reported evidence for these rings in 2010, analyzing WMAP and later Planck satellite data. They claimed to find dozens of concentric circles with statistically significant patterns, which they interpreted as Hawking points from the previous eon. Some of these circles appeared to overlap, consistent with the idea that multiple black holes evaporated in the same region of the previous universe before our Big Bang. Even so, these theories have caused a lot of debate. Several separate groups looked at the same CMB data again and said that the trends could have been caused by random changes. In a universe as big as ours, coincidences do happen, and it's very hard to tell the difference between a real signal and random noise. Some people also said that Penrose's scientific methods might have made the circles seem more important than they really were. As of now, there is no scientific agreement, and the CCC's CMB proof is still being hotly debated. Despite the skepticism, Penrose and his supporters have refined their search methods, continuing to claim new detections of Hawking points in updated Planck data. They argue that the clustering of these circles, their tendency to appear in overlapping groups, is unlikely to be random. If true, this would be a major blow to inflationary models, which predict no such features. The presence of these rings would strongly suggest that our universe inherited information from a previous aeon. The argument isn't over yet, but the next round of CMB tests might make things clearer. Missions with better detail and less noise, like Lightbird and the CMBS-4 project, might either prove or disprove these low variance rings. If these projects find consistent, statistically significant concentric circles across the sky, it would be one of the most important discoveries in the history of cosmology. It would show that the Big Bang wasn't the beginning of everything. Entropy and Weyl curvature in 300. According to Conformal Cyclic Cosmology, CCC, one of its main ideas is that the universe started out in a very low entropy state. This is one of the biggest mysteries in physics. The second rule of thermodynamics says that entropy, which is a measure of disorder, tends to rise over time. Still, the early world was very smooth and even, which means that entropy was very low. How could such a neat, well-organized start happen by itself? The Weyl curvature hypothesis is used by CCC to give a beautiful answer. Proposed by Roger Penrose long before 300, the Weyl curvature hypothesis argues that the early universe's extraordinarily low entropy comes from its gravitational smoothness. In general relativity, the curvature of space-time can be split into two components: Ricci curvature, which relates to matter and energy density, and Weyl curvature, which measures the shape or tidal distortions of space-time. High Weyl curvature corresponds to clumpy, irregular structures like galaxies or black holes, while low Weyl curvature describes a perfectly smooth, uniform space. The early universe, as seen in the cosmic microwave background, CMB, had almost zero Weyl curvature. It was astonishingly smooth. But why? CCC provides a natural explanation. In its framework, the end of one eon, trillions of years after all stars have burned out, eventually becomes conformally equivalent to the smooth beginning of the next. Black holes, which store enormous amounts of entropy, eventually evaporate via Hawking radiation, releasing their energy until no massive particles remain. In that distant future, only massless particles like photons and possibly gravitons exist. Without mass, space-time loses its scale. Size and time become meaningless, and the Weyl curvature effectively goes to zero. This conformal smoothing at the end of an eon becomes the low entropy starting point of the next. When conformal rescaling transforms the cold, empty future of one universe into the hot, dense beginning of the next, it automatically resets the entropy clock. The next eon inherits this gravitational smoothness as its initial condition, explaining why our universe started in such an ordered state without requiring fine-tuning. To put it more simply, 300 sees entropy as something that automatically resets when the eons change. This is because entropy doesn't rise in the normal way in a world made up of only massless particles. Conformal geometry doesn't care about size, so the theory says that the hot compression at the beginning of the next eon and the endless stretching of space in the previous one are the same thing. The old world doesn't leave a mess behind, it just fades away, making room for a new one. This idea also connects to Penrose's bold prediction that some information, specifically from black holes, could survive the transition. While most entropy dissipates, the final bursts of Hawking radiation from evaporating supermassive black holes may leave subtle imprints, carried over into the next eon, as the Hawking points discussed in 3C's CMB predictions. These points would be rare exceptions, tiny memories of the previous universe, preserved while almost all other details vanish in the conformal transformation. The Weyl curvature hypothesis within CCC also avoids one of the criticisms often leveled against inflation. Inflation explains the universe's smoothness by stretching space exponentially, but it doesn't explain why the conditions were right for inflation to begin. CCC, on the other hand, doesn't need finely tuned initial conditions. The end state of one eon naturally sets up the next, with low Weyl curvature arising as a direct consequence of mass loss over time. CCC's approach to entropy has sparked debate. Critics argue that while conformal rescaling might make the math work, it's unclear how entropy is truly erased. Even if massive particles eventually decay, some remnants, like dark matter or stable black hole remnants, might persist far into the future. CCC assumes that given enough time, these would either decay completely or become irrelevant at infinite expansion, but this is still speculative. Furthermore, the exact mechanism for transforming a cold, stretched-out universe into a hot, dense one remains mathematically elegant but physically untested. Black hole bounce, the black hole universe. What if the beginning of our universe wasn't from a single point of no return, but from the center of a black hole in another universe? This is the main idea behind the black hole bounce or black hole universe hypothesis. It's a big thought that every black hole might create a new universe on the other side of its event horizon. The extreme conditions at the heart of a black hole could cause a bounce instead of a singularity collapsing into nothingness. This would start the birth of a whole new universe. The concept emerges from the fact that general relativity predicts singularities inside black holes, just as it predicts one at the Big Bang. But singularities are problematic. They represent points where our equations break down, and densities go to infinity, which most physicists believe is a sign of incomplete physics, not an actual feature of reality. If something prevents true singularities, as quantum gravity theories suggest, then the interior of a black hole might behave very differently from what classical relativity predicts. Matter doesn't get squeezed into an infinitely small point when it goes into a black hole in this scenario. As densities get closer to the Planck scale, quantum gravitational effects cause a force that pushes against the collapse. In loop quantum cosmology, LQC, quantum geometry stops a singularity and starts a bounce, which is similar to what we see here. This bounce could cause a rapid expansion inside the black hole, which would be like a mini Big Bang and create a new world that can exist on its own. From the outside, we can only see the black hole eating things, but on the inside, a whole new universe might be taking shape. If this theory is correct, our own universe might be the product of such a process. Somewhere in a parent universe, a massive star collapsed into a black hole billions of years ago, and the bounce inside that black hole created the hot, dense state we call the Big Bang. The event horizon of that black hole would act like a one-way portal. Nothing from our universe can communicate back to its parent, and vice versa. For us, the Big Bang was a beginning, but from the perspective of the larger multiverse, it was just another black hole forming in a much bigger structure. Black holes could be natural seeds for universes, making a tree-like structure of universes. This is one of the most interesting ideas that comes from this thought. On paper, each black hole in every universe could make a new universe, which in turn would make more black holes that would make even more universes. Lee Smolin, a scientist, came up with the idea of cosmological natural selection. It even suggests that universes that are better at making black holes might have more of them than others in the multiverse. In a way, universes could evolve toward physical rules that help black holes form. This would make the fact that our universe's physics is friendly to black holes less of a surprise. This idea about a black hole universe also gives a nice answer to the question of what happened before the Big Bang. Time doesn't start at a single point. It just keeps going through the loop. The event horizon is crossed by matter and energy from the parent universe. They are squished to very high densities and then reborn as a new space-time that expands on its own. It looks like the Big Bang happened all of a sudden inside the baby universe, but from the outside, it's just the normal next step in the process of gravitational collapse. Testing this theory is, of course, difficult. By definition, we can't see beyond a black hole's event horizon. But there might be indirect hints. Some quantum gravity models predict that the earliest moments of our universe should carry subtle imprints of this bounce. For example, if our universe originated inside a black hole, the initial conditions might differ slightly from standard inflationary predictions, leaving unique signatures in the cosmic microwave background, CMB, or in the spectrum of primordial gravitational waves. These differences are subtle, but future high-precision observations may be able to spot them. It's also interesting to think that some properties of black holes in our world might show deeper connections between universes. If universes get some traits from their parent black holes, we might expect a statistical bias toward universes with physical constants that make the most black holes. This is just a guess, but it could be checked with data from astrophysics. White hole transition idea. What happens on the other side of bounces if black holes can create new universes? The white hole transition hypothesis is an interesting extension of this idea. It says that the collapse inside a black hole doesn't stop. It finally changes into a white hole, sending matter and energy flying into a new part of space-time. In this case, a black hole isn't a jail that never ends, it's a one-way tunnel, and the white hole phase is the start of a new universe. A white hole is the theoretical opposite of a black hole. While black holes pull in everything, even light, white holes are regions of space-time where matter and energy can only move outward. Nothing can enter, everything only exits. In classical general relativity, white holes are mathematically allowed solutions to Einstein's equations, but they have never been observed in nature. They were long considered purely hypothetical, strange mirror images of black holes that don't seem to exist in our universe. But in the context of quantum gravity and cosmology, they gain new life as potential birth points of universes. The white hole transition idea often appears in loop quantum gravity LQG research. In this framework, Space-time is made of discrete loops of geometry, and at ultra-high densities, quantum effects create a repulsive force that halts collapse. Instead of matter being crushed into a singularity, the collapse slows as quantum pressure builds. Eventually, this repulsion becomes strong enough to reverse the collapse, causing the black hole's interior to expand again. To an outside observer, the black hole may still look the same for a very long time, because time flows differently near the event horizon. But inside, the bounce progresses quickly, and at some point, the black hole may flip into a white hole. When that happens, all the matter and energy that fell into the black hole would be expelled in a sudden burst, creating conditions strikingly similar to a Big Bang. From inside the new expanding region of space-time, observers would see an event indistinguishable from the birth of a universe. To them, time would simply begin with a hot, dense state, just like our own Big Bang. This white hole transition model has some key advantages over traditional singularity-based cosmology. It provides a physical mechanism for the birth of universes without requiring creation from nothing. Instead, new universes recycle matter and energy from older ones through black holes. It also aligns with the idea that information isn't truly lost in black holes, a principle strongly suggested by modern physics. If black holes evolve into white holes, information could escape, not back into the parent universe, but into the new universe on the other side. Some scientists even think that quantum black holes in our own universe may already have changed into white holes. Some experts think that small black holes that formed in the early universe may have turned into white holes a long time ago, possibly leaving signs that can be seen. Certain types of fast radio bursts, or gamma-ray flashes, could be signs of the quick release of matter that has been trapped. Even though there isn't any proof of this yet, it's an interesting idea that is being looked into in astrophysics. The white hole transition idea also provides a natural way to explain the uniformity of the universe. Because the interior of the black hole undergoes extreme compression before the bounce, it smooths out irregularities. By the time the bounce triggers the white hole phase, the new universe starts off remarkably homogeneous, much like the conditions we see in our own cosmic microwave background. Figuring out how long this shift will take is one of the problems. The bounce and white hole expansion would seem to happen instantly to people in the new universe, but to someone in the parent universe, the process could take billions or even trillions of years because of how time bends so much near the black hole's edge. Something else that isn't clear is whether all black holes turn into white holes, or if there are conditions like mass, spin, or quantum geometry that decide which ones can create new worlds. It's hard to test this theory, but it's not impossible. What if white hole changes happen in our universe? They might leave special astronomical signs like strange energy bursts or leftovers of primordial black holes that don't behave like normal black holes. In the grand scheme of things, some aspects of the Big Bang, like certain patterns in gravitational waves or strange ways that matter is distributed, could point to a white hole beginning. Pre-Big Bang black hole remnants as dark matter. The thought that dark matter, the mysterious invisible substance that makes up about 85% of all matter, could be made up of black hole leftovers from a previous universe is one of the most interesting links between the physics of the universe before the Big Bang and the physics of our own. What if our universe came from a bounce or cyclic phase? It's possible that not everything from the earlier age was wiped out. Some things, especially black holes or quantum leftovers from them, may have made it through the transition and into our world. As dark matter, these old survivors could now drift through space in silence. The idea originates from theories in loop quantum cosmology (LQC) and bounce cosmologies. In these models, the singularity is replaced by a quantum bounce where extreme densities are finite and some structures may persist across cycles. While most matter and energy would have been redistributed during the bounce, certain ultra-compact objects, specifically primordial black holes, PBHs, or their leftover cores, could remain stable enough to survive the transition. But how would black holes make it through a bounce? The reasoning lies in quantum gravity effects. At the bounce, space-time doesn't collapse into a true singularity. Instead, as the universe contracts toward Planck densities, quantum repulsion halts further compression and reverses the collapse. Objects that are already extremely compact, like black holes, might remain intact if their masses are below a certain threshold. Their event horizons could shrink but not vanish, and as the universe rebounds, these black holes or their fossil remnants would expand into the new cosmic phase, along with everything else. Through Hawking radiation, big black holes would disappear over time, but smaller ones, especially those just above the Planck mass, might never disappear all the way. Carlo Rovelli and Francesca Vidotto, two of the world's top quantum gravity experts, said that these small leftover cores, which are sometimes called Planck mass relics, might stay stable for billions of years. If they made it through the bounce, they would be perfect candidates for dark matter, and the only way to see them would be through their gravitational pull. This idea has a lot of good points. First, strange new particles like WIMPs or axions are not needed to understand dark matter. They use well-known physics, like black holes and quantum gravity, to answer one of the biggest questions in astronomy. Second, it makes sense that dark matter only interacts through gravity, since black hole leftovers wouldn't have any electromagnetic interactions by nature. Third, the sheer number of these leftovers might be the same as the amount of dark matter that can be guessed from the way galaxies spin and the effect of gravity on lenses of light. Testing this hypothesis is tricky but not impossible. If dark matter is made of black hole remnants, we might detect its presence through microlensing events, temporary brightening of background stars when a dark object passes in front of them. Some microlensing surveys have already detected compact dark objects, but not in sufficient numbers to confirm the theory. Another possible signature could come from gravitational wave astronomy. If some of these ancient remnants merge, they could produce gravitational wave signals distinguishable from ordinary black hole mergers, particularly if the objects are unusually small. If some larger black holes from a previous universe survived, they might have seeded the growth of the first supermassive black holes we see at high redshifts. Observations of unexpectedly massive black holes in the very early universe, only a few 100 million years after the Big Bang, have puzzled astronomers. Pre-Big Bang black hole remnants could help explain how such enormous objects formed so quickly. Dark matter, possibly generated before the Big Bang. Could it be that dark matter wasn't just around after the Big Bang? What if it was there from the beginning? New research in theory says that dark matter may have been around before we could see it. It may have formed during a time before the Big Bang and left a hidden mark on the structure of the universe today. If dark matter is real, it will be more than just a puzzle of our time. It will be a holdover from a time when the universe didn't look the way it does now. The standard model of cosmology says that dark matter forms after the Big Bang, when the universe was still very cold and particles could condense. But a number of other models question this timing. Some people think that dark matter existed before the hot Big Bang phase. It could have been during a shrinking phase in a bounce cosmology, or even in a state of timelessness before inflation. If dark matter formed early, it would give us a unique look into the way physics worked before time began as we know it. Scalar fields are basic fields that can exist even when space-time is almost empty. One of the most interesting theories is based on them. A process called freeze-in could have made these fields make dark matter particles. In the more well-known freeze-out process, particles interact a lot before they lose their thermal equilibrium. But in freeze-in, dark matter is made so slowly and poorly that it never reaches equilibrium. It's important to note that this process can happen at very high temperatures, even before the universe went through its hot Big Bang phase. In pre-Big Bang inflationary models, scalar fields could have generated dark matter during the inflationary epoch itself, or even before inflation started. For instance, quantum fluctuations in a hidden dark sector might have produced particles that survived inflation's rapid expansion. These particles would have been diluted but not destroyed, leaving behind just enough to form the dark matter we detect today. Because they were created so early, their properties might differ from standard particle physics predictions, making them nearly invisible to direct detection experiments. Bounce cosmologies provide another pathway. In models like loop quantum cosmology, or the Eperotic Universe. The universe undergoes cycles of contraction and expansion. During the contracting phase, high-density conditions could have triggered exotic particle production. Some dark matter particles may have been stable enough to pass through the bounce unaffected, carrying information from a previous cosmic cycle into our current universe. If this is the case, some fraction of today's dark matter is literally older than the Big Bang, surviving across eons. Why consider pre-Big Bang dark matter at all? Because it solves several puzzling observational issues. For example, certain galaxy formation patterns and the distribution of small-scale cosmic structures are difficult to reconcile with traditional dark matter models. Pre-Big Bang dark matter could have slightly different velocity distributions or clustering behavior, subtly affecting how galaxies formed over billions of years. Additionally, the absence of signals in dark matter detection experiments hints that its interactions might be far weaker than expected, consistent with particles produced in an early, hidden phase of the universe. Researchers are exploring how to test these ideas. One promising avenue is through the cosmic microwave background, CMB. Pre-Big Bang dark matter would have left unique imprints in the form of slightly altered density fluctuations. Some models predict subtle deviations from the nearly scale-invariant spectrum of perturbations expected from standard inflation. Another possible clue comes from large-scale structure surveys. Dark matter born before the Big Bang might cluster differently, leaving faint but detectable differences in how galaxies are distributed across cosmic filaments. There's also the possibility of indirect detection through gravitational waves. If dark matter production was tied to violent pre-Big Bang events, such as a phase transition in a contracting universe or interactions in a pre-inflation vacuum, it might have generated a background of primordial gravitational waves. Detecting such a signal would not only provide evidence for pre-Big Bang physics, but also help determine whether dark matter truly predates our universe's hot phase. What field or process made dark matter if it existed before the Big Bang? Was it made during a moment of contraction, or did it exist in a vacuum that would never end? And how much of the dark matter we see today really comes from the beginning, rather than being made after the Big Bang? These are still open questions, but more theoretical work and new data may help us get answers. Observational signatures, CMB spectrum and tilt. The cosmic microwave background, CMB, which is the faint glow of the early universe, is one of the best places to look for clues about what happened before the Big Bang. This very old light, which came into being about 380,000 years after the Big Bang, has marks from the very beginning of the world. Different pre-Big Bang models, inflationary, hopping, or cyclic, predict the CMB's power spectrum and tilt in slightly different ways. This lets cosmologists see which models are more like the real world. The CMB power spectrum shows how temperature fluctuations are distributed across different scales in the sky. These fluctuations, which originated as tiny density variations in the early universe, grew into the galaxies and cosmic structures we see today. In standard inflationary cosmology, these fluctuations are predicted to be almost, but not perfectly, scale invariant. Scale invariance means the size of fluctuations looks the same across all scales, but inflation predicts a very slight tilt in the spectrum, known as the scalar spectral index, n subs. Observations from the Planck satellite show ns approximately 0.965, slightly below 1. Exactly as inflation predicts. But here's where things get interesting. Different models from before the Big Bang suggest different tilts. For instance, Eperotic and cyclic models cause changes during a time of slow contraction instead of fast expansion. The contraction makes the universe smoother and flatter, but it also causes perturbations that have their own tilt. These are usually more strongly blue-tilted, which means they have more power on smaller scales unless they are carefully changed, like in the new Eperotic cosmology. Similar to this, loop quantum cosmology LQC bounce scenarios suggest spectra that are almost scale invariant. However, the pre-bounce phase may introduce small oscillatory features or deviations at the largest scales. The amplitude of fluctuations at very large scales is another critical clue. Some bounce and cyclic models predict a suppression of power at the largest scales, corresponding to low multipole moments in the CMB. Interestingly, Planck data already shows a slight lack of power at these large scales compared to inflation's simplest predictions. While this could be a statistical fluke, it has given new life to pre-Big Bang alternatives. As such, suppression naturally arises in models with a contracting or bouncing phase before expansion. The running of the spectral index, or how the tilt changes with scale, is another important thing to look at. Most of the time, inflation only suggests a small run, but pre-Big Bang scenarios can show bigger changes, especially if the bounce or contraction involved complicated dynamics. Finding a lot of running would put normal inflation to the test and point to stranger physics from before the Big Bang. There's also the possibility of iso-curvature perturbations, fluctuations in the relative density of different components, like dark matter versus radiation. Inflation usually suppresses these, leading to purely adiabatic perturbations, but some bouncing and pre-Big Bang models predict small iso-curvature components. If future CMB measurements detect them, it could be a major signal of non-inflationary physics. CMB polarization gives us yet another view. The E-mode polarization pattern fits well with changes in temperature and inflationary forecasts. But the B-mode polarization pattern, which is caused by gravitational waves, is where things could get interesting. Inflation forecasts a background of primordial gravitational waves that are faint but can be found. These waves would leave a unique B-mode signature. On the other hand, many bounce and eperotic models say that gravitational waves will be very weak. Future missions like LIGHTBIRD or CMBS-4 might not find B-modes at the levels that would be predicted from inflation. If they do, this would strongly support scenarios from before the Big Bang. Spectral distortions in the CMB, tiny deviations from the perfect blackbody spectrum, could also hint at pre-Big Bang physics. Some bounce models predict unique energy injection patterns that might leave such distortions, which could be detectable by future experiments like PIXIE. So far, inflation remains consistent with current observations, but the differences between models are subtle, and more precise data may change the picture. For example, the slight large-scale anomalies in the Planck CMB maps, such as hemispherical asymmetry and unusual cold spots, are hard to explain with standard inflation, but could potentially be relics of a contracting or bouncing phase. Non-Gaussianities and perturbations. If the cosmic microwave background, CMB, is the best picture we have of the early universe, then the non-Gaussianities that are stored in its fluctuations are the fine print. These are the little statistical features that can tell us if the universe started with inflation, a bounce, or something even stranger. Non-Gaussianities are small differences from a perfect Gaussian bell curve distribution in the changes in the universe's density in the early universe. Based on standard inflation, these differences should be very small, almost unnoticeable. But a lot of pre-Big Bang models, like the Eperotic and bounce cosmologies, naturally suggest stronger, more unique non-Gaussian signatures. This makes them an important way to test what happened before the Big Bang. In cosmology, perturbations are the tiny density variations in the early universe that eventually grew into galaxies, clusters, and the cosmic web. Most of these perturbations are described as nearly Gaussian because inflation smooths out any irregularities, leaving only quantum fluctuations stretched to cosmic scales. But some processes, particularly those involving multiple fields, contracting phases, or non-standard dynamics, produce non-Gaussian distributions, leaving unique fingerprints in the statistical properties of the CMB and large-scale structure. The Eperotic and cyclic models are prime examples. During their slow contraction phase, the energy density of the universe is dominated by one or more scalar fields with steep potentials. In single-field Eperotic models, fluctuations are mostly smoothed out, resulting in almost no observable non-Gaussianity. However, in more realistic two-field versions, where one field drives contraction and the other generates perturbations, significant local-type non-Gaussianities are predicted. These appear as a distinctive three-point correlation pattern, the bispectrum, in the CMB, characterized by a parameter called FNL. While standard inflation predicts FANL close to zero, Eperotic models can produce values in the range detectable by next-generation CMB experiments. Bounce cosmologies, including loop quantum cosmology, LQC, and new Eperotic cosmology, also predict unique non-Gaussian features. In these models, perturbations are generated or amplified during the contracting phase and carried through the bounce into the expanding universe. The rapid change in background dynamics near the bounce can create oscillatory, non-Gaussian patterns, something inflation typically doesn't produce. Additionally, the ghost condensate bounce in new Eperotic cosmology allows nearly scale-invariant perturbations, while still leaving small but potentially detectable non-Gaussianities. Even Conformal Cyclic cosmology, CCC, has its own potential signatures. If Hawking points from evaporating black holes in a previous eon truly left imprints in our universe, they would appear as localized circular regions with unusual statistical distributions, a clear departure from Gaussian randomness. While CCC doesn't predict the same type of non-Gaussianities as bounce or eperotic models, its predicted anomalies, concentric low-variance circles, could be interpreted as a unique form of non-Gaussian structure. Observationally, it is hard but not impossible to measure non-Gaussianities. The Planck satellite has already put strong limits on many kinds of non-Gaussianity by proving that FNL is almost always equal to 0. Planck isn't very sensitive though, so some faint signals might still be hiding below its detection level. New projects like LIGHTBIRD and CMBS-4, as well as large-scale surveys of galaxies like Euclid and the Vera Rubin Observatory, will go much further than these. They will specifically look for non-Gaussianities and cross-correlations that rely on scale between the CMB and the distribution of galaxies. These could show signs of physics from before the Big Bang. The detection of significant non-Gaussianities would be a major blow to standard single-field inflation. While some exotic inflationary models can generate measurable non-Gaussianities, the shapes and amplitudes predicted by pre-Big Bang scenarios are often distinct. For example, Eperotic models typically predict large local-type non-Gaussianities, while bounce models might produce equilateral or oscillatory patterns. Pinpointing the exact shape of the bispectrum could therefore serve as a powerful diagnostic tool. There's also growing interest in primordial trispectrum measurements, 4-point correlations in the CMB. While much harder to detect, they could distinguish between different bounce and cyclic models, which sometimes produce strong trispectrum signals even when bispectrum signals are weak. Primordial gravitational waves. Gravitational waves from the beginning of time might help us figure out what happened before the Big Bang. These small waves in space-time were made in the very beginning of the universe. They are like messages from a time when light can't reach. Unlike photons, which were spread a lot before the cosmic microwave background, CMB, formed, gravitational waves move from their source almost without any problems. If we can find them, they might tell us if the universe went through a fast expansion, a slow contraction, or a quantum bounce. They might even prove that there was a time before the Big Bang. According to the standard model of inflation, initial gravitational waves should have formed as the universe grew very quickly. The fast stretching of spacetime made small quantum changes in gravity even stronger, forming a spectrum of gravitational waves that are almost always the same size. According to inflation, these waves should leave a clear pattern in the CMB. This pattern is called B-mode polarization, and it looks like the light in the CMB is spinning. The tensor-to-scalar ratio, R, is often used to show the magnitude of these waves. Depending on the inflationary model, inflation suggests a small value of R that might be able to be found. No definitive detection has been made. Experiments such as BICEP-2 once claimed to have found B-mode polarization consistent with inflationary gravitational waves, but the signal was later attributed to galactic dust. Current upper limits from the Planck satellite and BICEP/Keck collaborations put R below 0.036, already ruling out many high-energy inflation models. But this lack of detection doesn't just narrow inflation. It opens the door for alternative pre-Big Bang scenarios. Bounce and cyclic cosmologies generally predict much weaker or even negligible primordial gravitational waves. In models like loop quantum cosmology, LQC, and the new Eperotic cosmology, the contracting phase before the bounce strongly suppresses tensor perturbations. If the early universe was dominated by a slow contraction rather than rapid inflation, the production of gravitational waves would be minimal. This is a key distinction. If upcoming CMB experiments fail to detect primordial gravitational waves down to even lower values of R, it would be a strong point in favor of bounce or cyclic models over inflation. Bounce scenarios aren't entirely silent. Some versions of LQC predict unique blue-tilted gravitational wave spectra, meaning the waves are stronger at smaller scales, unlike inflation, which predicts more power at larger scales. Detecting such a blue tilt would be a clear signature of a bounce rather than inflation. Similarly, certain Eperotic models can produce non-standard polarization patterns or very specific frequency-dependent signals, distinguishable from the smoother inflationary background. Conformal Cyclic Cosmology, CCC, is another one. The CCC says there won't be a strong inflation-like gravitational wave background, but it does say that other gravitational marks from a long time ago might still be around. For example, bursts of gravity radiation could be caused by the final disappearance of supermassive black holes in the past universe. In 300, these events might show up as small changes in the CMB. These changes might have something to do with the Hawking points that Penrose says he has found. To detect these signals, scientists are building increasingly sensitive instruments. Upcoming missions such as Lightbird and CMB-S4 aim to measure B-mode polarization with unprecedented precision, pushing the detection threshold for R down to around 0.001. If they find a clear inflation-like signal, it will strongly favor inflationary cosmology. If they don't, it won't just be a null result. It will provide powerful evidence for alternative models where gravitational waves were suppressed. Future gravitational wave detectors like LISA, DECIGO, and the Einstein telescope could directly find primordial gravitational waves with different frequencies that go beyond the cosmic microwave background. Some bounce models suggest certain frequency bands that are too far away for the cosmic microwave background to pick up, but these instruments can still pick them up. A blue-tilted spectrum from a bounce, for instance, could make gravitational waves strong enough for LISA to pick up at millihertz frequencies. CMB anomalies and CCC tests. The cosmic microwave background, CMB, is often praised for how perfectly it matches the predictions of the standard cosmological model, but look closely and there are strange patterns, anomalies, that don't quite fit. These anomalies might be statistical flukes, or they could be the first subtle evidence of pre-Big Bang physics. Among the alternative models, Conformal Cyclic Cosmology, CCC, stands out for directly predicting some of these oddities, especially the controversial concentric low-variance rings known as Hawking points. If confirmed, these anomalies would be one of the strongest signs that our universe had a life before the Big Bang. The cosmic microwave background, or CMB, is likely to have random Gaussian fluctuations. These are very small changes in temperature that were caused by quantum jitters during inflation. But readings from Planck and WMAP have shown some strange things that don't quite fit the usual picture. Most of the southern hemisphere is warmer than usual, but there is a big cold spot. One half of the sky has slightly greater changes than the other. This is called hemispherical asymmetry. The alignment of low multipoles, also known as the axis of evil, makes large-scale patterns look like they are not truly random, but rather weirdly lined up. Standard inflation has a hard time explaining these strange events without using chance. Conformal Cyclic Cosmology, or CCC, sees them as natural marks left by things that happened in the past. CCC's most direct prediction, however, is the presence of concentric rings with unusually low temperature variance in the CMB. These rings, proposed by Roger Penrose and colleagues, are interpreted as the after-effects of black hole evaporation in the previous universe. According to CCC, when supermassive black holes finally evaporated via Hawking radiation near the end of the last eon, they released bursts of energy that carried over into our current eon. When conformally rescaled at the Big Bang, these bursts would appear as circular, smooth patches in the CMB, where temperature fluctuations are suppressed compared to their surroundings. Penrose's team claimed to have found dozens of such low-variance rings in WMAP and Planck data, some appearing in overlapping clusters, just as CCC predicts, since multiple black holes could have evaporated in the same region of the previous eon. These findings created a sensation when first announced in 2010, as no inflationary model predicts such features. The claims have been heavily debated. Multiple independent analyses argued that Penrose's statistical methods overestimated the significance of the rings. Simulations of random CMB skies have occasionally produced similar-looking circles, suggesting the patterns might just be chance alignments. Other researchers argue that even if the rings exist, they could be caused by unknown astrophysical effects rather than events from a previous universe. Despite the skepticism, Penrose and collaborators have continued refining their methods, analyzing newer Planck data. In 2018, they claimed to have identified Hawking points, small, circular hotspots about 3 to 5 degrees across that might be the final bursts of energy from evaporating black holes. These Hawking points would be the smoking gun for CCC, as no other mainstream cosmological model predicts them. Still, the controversy persists, as independent teams have not confirmed these findings with the same confidence. Beyond rings and Hawking points, CCC also offers an explanation for the low power at large angular scales, one of the most persistent CMB anomalies. Because CCC doesn't rely on inflation, which typically predicts smooth power across all scales, it naturally allows for suppressed fluctuations at the largest scales. This aligns intriguingly with Planck's observations, where the largest angular modes are weaker than expected. Future studies of the CMB will be very important in settling these arguments. Missions like Lightbird and CMB-S4 will give us maps with better resolution and less noise, which will let us confirm or rule out the low-variance rings and Hawking points. If these features hold up under more thorough examination, the CCC would become much more credible, and it might even beat inflation as the best account for how the universe started out. Reconciling Hubble constant tensions. The so-called Hubble tension is one of the biggest problems in modern cosmology. It is the growing difference between readings of the Hubble constant's H0 current expansion rate. Based on measurements made close to home using supernovae and Cepheid variables, a higher figure of about 73 km per second per megaparsec is suggested. Early universe predictions based on cosmic microwave background CMB data and the standard Kappa CDM lambda cold dark matter model, on the other hand, give a lower number of about 67. With more accurate data, this tension has only gotten stronger, which has made scientists wonder if new physics might be at play, maybe even effects from before the Big Bang. The Hubble constant tension is more than a technical disagreement. If both measurements are correct, it implies that the standard model of cosmology might be incomplete. Something about the early universe, before the release of the CMB, could have influenced its expansion in a way we don't yet understand. This has sparked a wave of new theories, including scenarios where pre-Big Bang physics directly affects today's observed expansion rate. There are some models that say the tension comes from early dark energy, which is a short period of dark energy-like activity right before the recombination. This early dark energy might have slightly changed the sound horizon, which is the scale left in the CMB by early sound waves. This would have made the Hubble constant that we get from measuring the CMB lower than the real value at this time. But where did this early dark energy come from? In some pre-Big Bang situations, like bounce cosmologies and eperotic models, dark energy or scalar fields could have changed over time and left such an imprint. In these models, fields that were active during a phase of contracting or bouncing might have stayed active during the early stages of growth, slightly changing how it moved. The James Webb Space Telescope, JWST, has recently added fuel to this debate. Its observations of extremely early galaxies forming sooner and faster than expected challenge the standard timeline of structure formation. If galaxies formed earlier than lambda CDM predicts, it could mean the universe expanded differently in its early stages, again hinting that something unusual happened either during or just before the Big Bang. Some cosmologists argue that this supports models where the initial conditions of the universe were set by a bounce or pre-Big Bang phase rather than a singular inflationary beginning. Loop quantum cosmology, LQC, also offers a potential explanation. In LQC, the bounce introduces modified Friedmann equations that change how the universe evolves at very high densities. These modifications could slightly shift the inferred value of H0 when matching early and late time observations. Similarly, Conformal Cyclic Cosmology, CCC, allows for the idea that the energy distribution from a previous eon, such as residual gravitational effects from evaporated black holes, might subtly alter large-scale structure formation, indirectly affecting Hubble constant estimates. Testing these ideas requires cross-checking data from different epochs of the universe. If the Hubble tension is caused by new early universe physics, we should find additional discrepancies in other cosmological parameters, such as the sound horizon or baryon acoustic oscillations. Surveys like DESI, Dark Energy Spectroscopic Instrument, and SPHEREX are now mapping the large-scale structure of the universe with extreme precision, aiming to determine whether the tension can be explained by late-time systematics, or if it truly points to exotic early or pre-Big Bang physics. You could also look for hints of events that happened before the Big Bang in the CMB lensing signal, or in the way that groups of galaxies are spread out. If early vector fields or dark energy left over from a bounce phase had an effect on expansion, it might show up as small changes in how the biggest galaxies group together. Galaxy Survey missions, SPHEREX and DESI. We need to make a very detailed picture of the universe that shows not only how it is now, but also how it has changed over time if we want to find out what happened before the Big Bang. In fact, two very advanced projects, SPHEREX and DESI, are made to do just that. Even though neither was designed to study physics before the Big Bang, they are very good at measuring the past of the universe's expansion and its large-scale structure. This means that they could be very useful for testing different cosmological models, such as inflation, bounce cosmologies, and cyclic scenarios. The spectrophotometer for the history of the universe, epoch of reionization, and ICE's explorer, SPHEREX, is a NASA mission scheduled for launch soon. Its primary goal is to perform an all-sky spectral survey of hundreds of millions of galaxies, spanning a wide range of redshifts. Unlike imaging telescopes that simply take pictures, SPHEREX will measure the spectral fingerprints of galaxies, the distribution of light across different wavelengths, allowing astronomers to determine their redshifts with remarkable accuracy. By building this massive 3D map of the cosmos, SPHEREX will reveal how structures formed and evolved over billions of years. Quantifying baryon acoustic oscillations, BAOs, the small sound wave patterns left behind by the distribution of galaxies, will be one of SPHEREX's major contributions. As a cosmic master, BAOs show how fast the universe grew at different points in time. Scientists can test whether the standard expansion history suggested by inflation is correct by comparing BAO measurements from different times. If it is not, they can see if other scenarios, like early dark energy, bounces, or evolving scalar fields, fit the data better. Small changes in the sound horizon scale are often predicted by models from before the Big Bang. This is especially true if the early universe contracted or had strange physics happen before or instead of inflation. SPHEREX will also provide a unique test for inflationary models through its measurement of non-Gaussianities in galaxy clustering. While most large-scale structure is nearly Gaussian, small deviations in how galaxies cluster could indicate exotic early universe physics. Eperotic and bounce models, for instance, often predict distinct non-Gaussian patterns different from inflation. SPHEREX's vast dataset could either confirm the inflationary predictions of almost perfectly Gaussian structure or reveal subtle anomalies hinting at a pre-Big Bang phase. The Dark Energy Spectroscopic Instrument, DESI, already operational, complements SPHEREX by focusing on high-precision spectroscopy of millions of galaxies and quasars. DSE's primary goal is to study dark energy by mapping the expansion history of the universe with unmatched detail, but its results have significant implications for early universe physics. By pinning down how the expansion rate evolved, DESI can indirectly test whether dark energy behaved differently in the early universe, something that bounce and cyclic cosmologies often require. Improving readings of the Hubble constant tension will be one of the most important things that DESI does. If the large-scale structure data from DESI keeps showing differences between the rates of early and late-time expansion, it could make the case for new physics beyond normal degrees, CDM, stronger. For example, bounce models suggest that the expansion equations will change early on, and cyclic scenarios allow dark energy to change, which could be seen in DESI's galaxy clustering data. DESI is also mapping the large-scale distribution of matter across cosmic filaments, providing another indirect probe of pre-Big Bang physics. Some bounce models predict slight differences in how structures form, particularly at the larger scales, because initial density fluctuations are inherited from a contracting phase rather than stretched by inflation. Detecting these differences requires enormous statistical samples, exactly what DESI excels at providing. When combined, SphereX and DESI will create the most detailed 3D map of the universe ever constructed, spanning from the nearby cosmos to galaxies more than 10 billion light-years away. This joint dataset will allow cosmologists to test whether the early universe was perfectly smooth and inflationary, or whether it carries hidden scars from a previous cosmic cycle. Through their indirect effects on large-scale structure, both projects will help look for signs of the first gravitational waves. Inflation models say that changes in density and gravity waves are connected in a certain way, while bounce and eperotic models say that the signals will be much weaker or tilted to the blue. Sphere and DESI can help prove or disprove these ideas by looking into how galaxies group together and how structures changed over time. Implications of evolving dark energy. Dark energy is one of the greatest mysteries in cosmology, the unknown force driving the accelerated expansion of the universe. In the standard lambda CDM model, dark energy is treated as a constant, often identified with Einstein's cosmological constant. But what if dark energy isn't constant at all? What if it evolves over time, changing its properties across cosmic history? Such a scenario wouldn't just tweak our understanding of the universe's future. It could also reveal clues about its past, including what happened before the Big Bang. In evolving dark energy models, the universe's expansion is not simply a smooth, steady acceleration. Instead, dark energy's strength and behavior can shift, possibly even reversing from expansion to contraction in the distant future. This has huge implications for bounce and cyclic cosmologies, which rely on dark energy to control the timing of contraction phases and bounces. In cyclic models inspired by Eperotic cosmology, for example, dark energy plays a dual role. During the current expansion, it pushes galaxies apart and smooths out space-time. But over extremely long timescales, the properties of dark energy could change, weakening until gravity takes over again. Once that happens, the universe would slow its expansion, reverse into a contracting phase, and eventually bounce, starting a new cycle. Without evolving dark energy, this cosmic rhythm wouldn't be possible. Some loop quantum cosmology LQC scenarios also predict evolving dark energy near the bounce. In these models, dark energy might behave differently at high densities, interacting with quantum geometry effects. As the universe contracts toward Planck densities, dark energy could become repulsive, helping to trigger the bounce itself. This would mean dark energy isn't just a late-time phenomenon, but has been influencing the universe's dynamics from its earliest, or even pre-Big Bang, phases. There's also a deeper connection between evolving dark energy and the Hubble constant tension. Several studies have suggested that introducing an early phase of dark energy, active just before or during recombination, could help reconcile the conflicting measurements of the universe's expansion rate. Interestingly, this early dark energy could naturally arise in bounce or cyclic models, where scalar fields transition smoothly across cosmic cycles. But evolving dark energy doesn't just have implications for the past. It also changes predictions about the future fate of the universe. In the standard model, the cosmos will expand forever, cooling into a big freeze. However, if dark energy evolves into a negative or contracting phase, the universe could experience a big crunch, collapsing again into a high-density state. In bounce models, this collapse would simply be the beginning of another expansion phase, turning the big crunch into a big bounce. In this way, the behavior of dark energy could literally determine whether our universe has a one-time beginning and end, or an eternal cyclic history. Testing whether dark energy evolves is one of the major goals of current and upcoming surveys. Missions like DESI, SphereX, and the Euclid Space Telescope are measuring the expansion rate of the universe at different epochs with unprecedented precision. If dark energy is constant, the data should perfectly match a cosmological constant. But if it evolves, we might see subtle deviations. For instance, changes in the equation of state parameter, W, which describes the ratio of dark energy's pressure to its energy density. In the standard model, W equals -1. Any deviation, especially if it changes over time, would indicate evolving dark energy. The implications for pre-Big Bang physics are enormous. If dark energy evolves, it strengthens the case for cyclic or bouncing universes. A dynamic dark energy component could be the mechanism that controls cosmic phases, ensuring that the universe doesn't just expand forever, but eventually collapses and restarts. Even inflationary cosmologists are considering whether dark energy might be connected to the same fields that drove inflation, possibly remnants of a pre-Big Bang scalar field that persisted into today. Big crunch versus big freeze versus big bounce. What will happen to the world in the end? Will it keep growing until it turns into a cold, empty void? Will it go in the opposite direction and fall apart? Or will it shrink, bounce, and start over in an endless circle of birth and death? The big freeze, the big crunch, and the big bounce are not only predictions about the future, they also hold secrets about the past, like whether the Big Bang was really the start of something new or just a part of a much bigger story. The big freeze, also called the heat death, is the standard prediction under the lambda cold dark matter model. In this scenario, dark energy, treated as a cosmological constant, continues to drive accelerated expansion indefinitely. Over trillions of years, galaxies drift apart faster than light, stars burn out, and black holes evaporate through Hawking radiation. Eventually, the universe becomes a dark, empty void filled only with low-energy photons and sparse particles. Time continues forever, but nothing meaningful happens. While bleak, this scenario fits perfectly with current observations, which suggest dark energy has remained constant for billions of years. The big freeze assumes dark energy never changes. If dark energy evolves, the story could end very differently. In some models, dark energy might weaken over time or even reverse, allowing gravity to regain control. This leads to the big crunch, where cosmic expansion slows, stops, and reverses. Galaxies fall back together, stars and black holes collide, and the universe contracts into an extremely dense, hot state. In classical general relativity, this would end in a singularity, a catastrophic endpoint where space and time themselves collapse. But modern theories like loop quantum cosmology, LQC, and new Eperotic cosmology replace the singularity with something far more interesting, the Big Bounce. In these models, when the universe contracts to near-Planck densities, quantum gravity effects generate a repulsive force, preventing infinite collapse. Instead, the universe reaches a minimum size and rebounds, expanding again in a new cycle. This turns the big crunch from a final end into a transitional phase, one bounce in an eternal sequence of contractions and expansions. The big bounce changes not only the future, but also the past. There is a good chance that the universe bounced before the Big Bang, since it can imagine the future. It was just the latest bounce in a cosmic loop that will never end. Most signs of the previous cycle may be erased by each new one, but small hints may still be left behind, such as less power in the CMB or strange gravitational wave signatures. Eperotic and cyclic models take this even further, suggesting that cycles can repeat forever. In these scenarios, the universe undergoes a slow contraction phase before each bounce, smoothing out irregularities and flattening spacetime. Dark energy plays a key role, first driving expansion and later allowing the reversal into contraction. This cyclic view eliminates the need for a true beginning or singularity, replacing it with an eternal cosmic rhythm. The behavior of dark energy has a lot to do with which of these outcomes is right. The big freeze will happen if it stays the same or gets stronger. If it gets weaker or changes direction, a big crunch could happen. If quantum effects get in the way, there would be a bounce. By looking at the sky, projects like DESI, SPHERE, and EUCLID are trying to find out if dark energy changes over time. We can't be sure what will happen in the world in the future if the cosmological constant changes even a little. Challenges to standard cosmology from new CMB sources. The cosmic microwave background, CMB, has been the best way to test cosmological theories for a long time. Many people say that its almost perfect match with expectations from the standard CDM model is one of the biggest scientific achievements of our time. But as we get better at observing, new CMB oddities and unexpected astrophysical sources are starting to call the usual story into question. Some of these differences could point to deeper physics, maybe even events that happened before the Big Bang that the standard model doesn't explain. James Webb Space Telescope, JWST, finds very early, bright galaxies. This is one of the biggest problems we've had to deal with recently. It looks like these galaxies formed and grew much faster than what KCDM says they should have. If they were proven to exist, it could mean that the first changes in density, which are the building blocks of structure, were stronger or behaved in a way that wasn't predicted. Since those changes are recorded in the CMB, any change from that pattern suggests we might be missing some information about the very beginning of the past of the universe. Standard inflation might not be able to explain these strange events as well as bounce or cyclic models, which usually forecast different initial perturbation spectra. Another issue involves newly identified foreground sources that may subtly distort how we interpret CMB data. For decades, cosmologists have carefully separated the CMB's faint microwave glow from emissions by galaxies, galaxy clusters, and interstellar dust. But as we push for greater precision, we're finding that red, early star-forming galaxies, once thought too faint to matter, may be contaminating large-scale CMB measurements. These galaxies emit microwave and infrared radiation that could mimic or mask the true CMB fluctuations, particularly on large angular scales where some of the standard model's tensions, like low multipole anomalies, already exist. If these background sources are having a bigger effect on the data than we thought, it opens up two options. Either the problems with the standard model are just the result of wrongly interpreting the data, or, and this is more interesting, the problems are real and point to physics beyond the standard model. For instance, the CMB's large-scale power suppression might not be a result of the way it was observed. It could be proof of a phase before inflation or a universe shrinking before a bounce, both of which naturally lead to large-scale power suppression. The early galaxy input on the CMB is another issue. As our understanding of how galaxies form grows, some scientists say that big galaxies that were making stars in the early universe may have had an effect on the CMB by heating the gas around them or using gravitational lensing. This might slightly change the CMB's temperature and polarization patterns, sending us signs that we might think are from the beginning of time. But if these effects can be accurately modeled, they might also show if some of the CMB's strange traits, like the hemispherical asymmetry or cold spots, are just astrophysical artifacts or real remnants of the early universe. Models from before the Big Bang say that the cosmic microwave background will have certain signatures. These signatures might still be there even after new astronomical sources are taken into account. Loop quantum cosmology, or LQC, says that a cosmic bounce leaves behind small changes in the CMB power spectrum. The Eperotic and cyclic models say that there are unique non-Gaussian patterns that might be hiding beneath what we think of as noise right now. Conformal Cyclic Cosmology, or CCC, even predicts patterns in certain areas called Hawking points that would not be erased by normal foreground corrections. But we will need a lot more accurate data to tell the difference between real primordial signs and simple contamination. This is where new missions like CMBS-4, Lightbird, and the next wave of ground-based observatories will come in handy. Because they are so sensitive, we may finally be able to tell the difference between real cosmological signs and background noise. It's very important because every change in how we understand CMB data has a direct effect on how we rebuild the universe's earliest moments. If the anomalies go away after all foreground inputs are taken away, it will support the standard inflationary Big Bang. But if they stay, especially if they fit what bounce or cyclic models say should happen, it could be the first solid proof of physics before the Big Bang. Role of red early star-forming galaxies. Cosmologists have used the cosmic microwave background, CMB, as a nearly perfect view into the Big Bang to learn more about the early universe. New information, however, suggests that the picture may not be as clear as we thought. Some of the oldest and most active galaxies in the universe are red, early star-forming galaxies that could be slightly changing CMB readings, making it harder to figure out what the signals mean. This problem is not just a technical one. It could either explain some long-standing CMB oddities or show secret signs of physics before the Big Bang. These galaxies, often rich in dust and forming stars at extremely high rates, emit large amounts of infrared and submillimeter radiation. This emission can contaminate CMB observations, especially at the same frequencies that telescopes like Planck and WMAP use to study the faint microwave glow from the early universe. The problem grows worse because these galaxies are clustered along large-scale structures, meaning their emissions don't average out uniformly. Instead, they can subtly alter the statistical patterns of CMB fluctuations. The potential impact of these galaxies has grown more significant with recent observations from the James Webb Space Telescope, JWST. JWST has identified unexpectedly massive red star-forming galaxies existing just a few hundred million years after the Big Bang. Their existence challenges standard structure formation models, which struggle to explain how so much star formation could occur so early. But beyond the galaxy formation puzzle, these early galaxies might be skewing our view of the CMB itself. How could these factors influence our understanding of early universe physics? There are several possibilities. First, distortion of large-scale temperature fluctuations. The CMB's largest angular scales show surprisingly low power compared to standard inflationary predictions. Some of this anomaly could be caused by unresolved infrared sources, such as red, star-forming galaxies, introducing spurious correlations. If that's true, some of the so-called CMB anomalies might not be primordial at all, but rather late-time astrophysical effects. Second, confusion with non-Gaussian signatures. Many pre-Big Bang models, like Eperotic Cosmology and loop quantum cosmology, predict distinctive non-Gaussian patterns in the CMB. But clustered infrared emissions from star-forming galaxies can mimic, or even mask, these same patterns. If we don't properly account for this contamination, we might mistakenly dismiss genuine pre-Big Bang signatures as noise, or worse, interpret ordinary galaxy emissions as evidence for exotic physics. Third, impact on gravitational lensing maps. These galaxies trace the large-scale structure of the universe and correlate with gravitational lensing signals. Since lensing slightly distorts the CMB's temperature and polarization patterns, improper modeling of these galaxies can bias key measurements, like the tensor-to-scalar ratio, a crucial parameter for testing inflation against bounce models. A misinterpretation here could either falsely favor inflation or obscure evidence for alternative scenarios. Finally, hints about pre-Big Bang conditions. Ironically, the very existence of these early galaxies might itself point to unusual physics before the Big Bang. Bounce and cyclic cosmologies often predict a slightly different spectrum of primordial fluctuations, potentially leading to earlier and more efficient structure formation. If standard lambda CDM struggles to explain why these massive dusty galaxies appeared so quickly, it may not be a coincidence. Their presence could be a fingerprint of initial conditions set during a pre-Big Bang phase. Observations made in the future will be very important for separating these options. High-precision maps of the locations of star-forming galaxies will be made by missions like SPHERE and Euclid. This will help cosmologists model their contributions and take them out of CMB data more accurately. If the CMB anomalies go away after these fixes, it would make the case for normal inflationary cosmology stronger. But if the strange things keep happening even after taking into account galactic contamination, it means they are really primordial. They could be proof of a bounce, a cyclic past, or even leftovers from a previous eon, as the Conformal Cyclic cosmology theory suggests. Mysterious Saleh particle claim. There are many ideas that try to explain what happened before the Big Bang. Some are based on solid mathematics, while others are still based on a lot of guesswork. A Saleh particle is one of the strangest and most controversial ideas. It is a supposed basic part of the universe that some fringe thinkers say could explain what caused the Big Bang. The Saleh particle theory is interesting because it says the Big Bang might have started with interactions between strange particles that were already there, rather than a singularity or a quantum vacuum fluctuation. However, this theory is not widely accepted in standard physics. The Saleh particle, proposed by independent researcher Mohammed Saleh, is claimed to be a subphoton particle, a fundamental building block smaller and more basic than photons or quarks. According to this hypothesis, these particles filled the pre-Big Bang vacuum in an ultra-stable state. Unlike ordinary particles, they were not bound by the same energy constraints as the Standard Model's particles. Instead, they existed in what Saleh describes as a hyperdense pre-cosmic fluid with nearly zero entropy. At some point, an instability in this fluid supposedly triggered a catastrophic release of energy, igniting the rapid expansion we call the Big Bang. In this framework, the Saleh particles acted almost like a primordial fuel, storing enormous amounts of energy in a hidden state. Once they destabilized, their interactions generated all the known particles of the Standard Model, seeding the early universe with matter, radiation, and dark components. Proponents claim this could explain why the universe began in such a hot, dense state without requiring a singularity or quantum tunneling event. What makes the idea even more speculative is its claim to potentially explain dark matter and dark energy. The Saleh particle, being nearly massless and weakly interacting, could persist as a relic from the pre-Big Bang state, forming part of the mysterious dark matter that permeates galaxies. Additionally, the residual energy field associated with Saleh particles might manifest as the repulsive force we attribute to dark energy, providing a unifying explanation for multiple cosmic mysteries. Supporters of the Saleh particle hypothesis often point to certain CMB anomalies as indirect evidence. They argue that if Saleh particles influenced the very earliest expansion, they might have left behind subtle, non-Gaussian imprints in the CMB. Some even speculate that the low power observed at large scales or the hemispherical asymmetry could be explained if the Big Bang began as a localized phase transition in a Saleh particle-dominated pre-cosmic fluid. The theory faces significant criticism and skepticism from the mainstream scientific community. For one, it lacks a mathematically rigorous framework. The properties of the Saleh particle are not derived from established quantum field theory or string theory, but are instead described qualitatively, with no clear equations predicting measurable phenomena. Furthermore, no experimental evidence for subphoton particles exists, and particle accelerators like the LHC have found no sign of anything resembling the proposed Saleh particle. Even so, fringe theories like these persist because they try to answer some of the deepest, unresolved questions in cosmology. What caused the Big Bang to ignite in the first place? Why did the universe begin in such a low entropy, highly ordered state? And what is the true nature of dark matter and dark energy? From a more positive point of view, the Saleh particle idea is conceptually similar to other popular ideas from before the Big Bang. String gas cosmology, for example, imagines a state before the Big Bang that is full of strange fundamental things. In the same way, some forms of bounce cosmologies and emergent universe models say that the change from contraction to expansion was caused by a medium or field that was already there. The Saleh particle claim is still just a guess, while those ideas are mathematically consistent with what we know about physics. Testing such an idea would require evidence far beyond what we currently have. If Saleh particles exist, they might produce detectable signatures in high-precision cosmological data. For instance, very specific patterns in CMB non-Gaussianities, unique distributions of primordial gravitational waves, or unusual properties of dark matter. So far, no such evidence has been found. Even fringe hypotheses sometimes play a role in pushing science forward by encouraging new ways of thinking about old problems. The Saleh particle claim may never gain acceptance, but it reflects a broader trend in cosmology. The growing willingness to consider that the Big Bang might not have been a true beginning, but a transition from some pre-existing state, whether that state involved quantum geometry, cyclic brains, or, in the wildest scenarios, a sea of exotic primordial particles. Critique of non-standard plasma cosmology. Plasma cosmology was one of the main alternatives to the Big Bang as a way to explain how the world began. Plasma cosmology was proposed and backed by scientists like Hannes Alfvén. It imagined a universe that would last forever, stay the same, or slowly change over time, with electromagnetic forces, not gravity, creating the structures of the universe. Plasma cosmology said that the universe had always been there, with huge networks of charged particles and electric currents building galaxies, stars, and other structures over an endless amount of time. Plasma cosmology was an interesting idea, but current observations, especially those from the cosmic microwave background CMB, have mostly ruled it out. However, it still comes up sometimes in discussions about other cosmologies. The core idea behind plasma cosmology is that the universe is dominated by ionized plasma, electrically charged particles that respond strongly to magnetic and electric fields. In this framework, large-scale cosmic structures are shaped primarily by Birkeland currents, enormous electric currents flowing through intergalactic space. Galaxies, according to this theory, are not formed by gravitational collapse within dark matter halos, but by plasma filaments twisting into structures under electromagnetic forces. Because plasma can self-organize into stable filamentary patterns, proponents argued that the universe didn't need an explosive beginning or mysterious dark components to explain its structure. The idea that there was no such thing as a cosmic singularity was one of the best things about plasma astronomy. There would have been no need for a creation event, like the Big Bang, if the universe had always been in a state of plasma. It's possible that the universe has no starting or end and is infinite in both space and time. People who didn't like the idea of time starting suddenly liked this. As observational data accumulated, plasma cosmology failed multiple critical tests. The strongest blow came from the discovery and detailed measurement of the cosmic microwave background. Plasma cosmology struggled to explain why the CMB is nearly a perfect blackbody spectrum, exactly what you would expect from a hot, dense early universe cooling over billions of years. Attempts to reinterpret the CMB as merely scattered starlight or plasma radiation failed because they could not reproduce the uniformity and precise temperature fluctuations observed by COBE, WMAP, and Planck. The model also cannot explain the observed abundance of light elements like helium, deuterium, and lithium. Big Bang nucleosynthesis provides precise predictions for these abundances, which match observations almost perfectly. Plasma cosmology has no comparable mechanism for how these elements formed naturally across the entire universe. Plasma cosmology struggles with galaxy evolution and redshift observations. The large-scale structure of the universe, as mapped by galaxy surveys, fits remarkably well with predictions from the Big Bang model, where dark matter and gravity dominate. Plasma cosmology's electromagnetic explanations, while interesting for local plasma phenomena, don't account for the statistical distribution of galaxies or the observed baryon acoustic oscillations imprinted in their clustering. New data about cosmic acceleration and dark energy makes the plasma approach even less convincing. Finding that the universe is expanding faster, likely due to some kind of dark energy, doesn't make sense in a universe that is made of plasma. KCDM astronomy, on the other hand, fits it perfectly. While mainstream science has moved past plasma cosmology, it's not entirely without merit. On smaller scales, plasma physics remains crucial for understanding astrophysical phenomena such as solar flares, auroras, and certain filamentary structures in galaxies. Alfvén's work on plasma behavior earned him a Nobel Prize, But applying those principles to the entire universe has proven inconsistent with modern evidence. So why do some discussions of different cosmologies still bring up plasma cosmology when they talk about physics before the Big Bang? Mostly because it's an early attempt to think about a universe that will never end, which is an idea that can be found in more current models like Conformal Cyclic Cosmology, CCC, or Cyclic Eperotic Cosmology. But unlike those models, plasma cosmology doesn't have a framework for quantum gravity or bounce physics that is consistent with math, and it also doesn't make accurate statements that can be tested and match what we see. Current failures and unanswered gaps. Modern cosmology has come a long way, including making accurate predictions about the Big Bang and inflationary models. However, there are still a lot of big questions that standard cosmology can't explain. These gaps are not just small details, they go to the heart of what we know about how the world began, what it is made of, and how it has changed over time. They also don't rule out the idea that physics from before the Big Bang, such as bounces, cyclic phases, or other strange situations, might be needed to fully understand the universe. The problem of the starting singularity is one of the most obvious holes. A singularity is a point of infinite density and curvature where space-time and the rules of physics don't work. This is where the standard Big Bang model starts. There is no way for general relativity to explain what happens at that point, so we have no idea how or why the universe started. This problem isn't solved by inflation either. It just changes the question to what caused inflation and what was there before it. This is a big reason why people come up with other theories, like Conformal Cyclic Cosmology, CCC, or Loop Quantum Cosmology, LQC, which see a smooth transition from a past eon instead of a singularity. Another major failure lies in explaining dark matter and dark energy. While LCDM successfully describes their effects on cosmic structure and expansion, it provides no insight into their fundamental nature. We don't know what dark matter particles are, despite decades of searches in underground detectors and at particle accelerators. We also don't know why dark energy exists, why it has the value it does, or why it began dominating the universe's expansion only in the last few billion years. Pre-Big Bang models sometimes offer alternative ideas, such as dark matter being composed of black hole remnants from a previous universe, or dark energy being tied to scalar fields active in a pre-Big Bang phase. But none of these ideas have been confirmed. The Hubble constant tension remains one of the most pressing gaps in standard cosmology. Early universe predictions from the CMB give a lower Hubble constant than late-time measurements based on supernovae and Cepheids. If this discrepancy isn't due to measurement errors, it could mean that something unusual happened in the early universe, possibly an early dark energy phase or pre-Big Bang effects that altered the initial conditions. Bounce and cyclic models naturally allow for evolving dark energy or modified early expansion rates, making them attractive candidates to explain this tension. There are also lingering CMB anomalies that standard inflation struggles to explain. The low power at large angular scales, hemispherical asymmetry, and the infamous cold spot don't fit neatly into the inflationary framework. While these could be statistical flukes, they might also be relics of pre-inflationary or pre-Big Bang physics. Models like CCC even predict specific features, such as concentric low-variance rings, Hawking points, which are not expected under standard cosmology. The origin of the primordial density fluctuations, the seeds of all cosmic structure, also remains only partially understood. Inflation attributes them to quantum fluctuations stretched across space, but it requires carefully tuned initial conditions to work correctly. Why did inflation start at all, and what determined its duration and energy scale? Pre-Big Bang alternatives, such as Eperotic contraction or string gas cosmology, attempt to explain these fluctuations differently, sometimes predicting unique non-Gaussian patterns or suppressed power at certain scales. Determining which model is correct requires more precise data than we currently have. There are still some unanswered academic questions about inflation as well. There are problems with fine-tuning the theory. For the observed smoothness and flatness to happen, specific potential shapes for scalar fields are needed. Some versions say that primordial gravitational waves have too much power, which has already been shown to be false by measurements. Other versions allow for endless inflation, which brings up its own problems, such as the idea of an infinite multiverse, where it's impossible to know what will happen next. Because of these problems with ideas, scientists look for other models that might be simpler and not as well tuned. The lack of a complete quantum theory of gravity is perhaps the deepest gap of all. We have no experimentally verified framework combining general relativity with quantum mechanics. Without it, we can't describe what happened at Planck scale densities, exactly the regime relevant to the Big Bang, or any bounce that might have preceded it. Theories like LQC, string theory, and other quantum gravity approaches are promising, but they remain incomplete and untested. We still don't know what started the growth, what caused inflation, even if it did happen, what changed during the recession phase, even if there was a bounce. Some models, like 300, say there is no real beginning and instead see an endless series of cycles. Some people suggest quantum tunneling from a state of emptiness, but these are still just theories until they are proven by direct observation. Comparing predictions across competing cosmologies. To figure out what happened before the Big Bang, we can't just guess about different models. We have to compare their specific testable statements. Different theories, such as inflation, loop quantum cosmology, LQC, Eperotic and cyclic cosmologies, Conformal Cyclic cosmology, CCC, and the black hole bounce, BH bounce scenario, have very different ideas about how the universe came to be. However, they can be compared by looking at what they say about important things that can be seen, like the CMB spectrum, and any oddities, non-Gaussianities, gravitational waves, structure formation, and even the end of the universe. Inflation remains the dominant theory because it fits most existing data. It predicts an almost perfectly scale-invariant CMB spectrum with a slight red tilt, consistent with Planck's measurement of a scalar spectral index near 0.965. It also predicts a nearly Gaussian distribution of fluctuations, with non-Gaussianities so small they are essentially undetectable. Primordial gravitational waves are a major inflationary prediction, expected to leave a measurable B-mode polarization in the CMB if the inflationary energy scale was high enough. So far, no such signal has been confirmed, but ongoing searches by LightBird and CMBS-4 may soon provide an answer. Inflation also predicts no significant cyclic history. The universe simply expands forever, likely ending in a big freeze. Loop quantum cosmology takes a radically different approach, replacing the singularity with a quantum bounce. Instead of beginning in a singular state, the universe contracts to a minimum volume and rebounds. Its predictions include a nearly scale-invariant CMB, but with possible small oscillatory features at large angular scales, features that could explain the low power observed in Planck data. LQC strongly suppresses primordial gravitational waves compared to inflation, predicting a very low tensor-to-scalar ratio, and in some cases, a slightly blue-tilted gravitational wave spectrum. If future CMB measurements continue to fail to detect inflationary gravitational waves, LQC will gain credibility. Unlike inflation, LQC implies the universe may have undergone many cycles, possibly extending infinitely into the past and future. The Eperotic and cyclic cosmologies are even more distinctive. The Eperotic scenario relies on a slow contraction phase before the bounce, which naturally flattens and smooths the universe. It predicts unique non-Gaussianities, often larger than inflation allows, particularly in two-field models. Its gravitational wave background is extremely weak, much weaker than inflation's, because the slow contraction phase suppresses tensor fluctuations. If observations confirm a very low tensor-to-scalar ratio, it would support this scenario over inflation. In its cyclic form, this model envisions an eternal sequence of contractions and expansions, meaning our Big Bang was not a unique event, but just the latest bounce. Conformal cyclic cosmology stands apart with its radical approach. It doesn't use bounces at all, but instead links the end of one universe, an eon, to the beginning of the next via conformal rescaling. Its most famous prediction is the presence of Hawking points, small circular hotspots in the CMB caused by black hole evaporation in the previous eon. CCC also predicts suppressed power on the largest CMB scales, consistent with some existing anomalies. Gravitational waves from inflation are not expected in this model, but bursts of gravitational radiation from evaporating black holes in the previous eon might leave subtle traces. If future CMB surveys confirm concentric low-variance rings or Hawking points, CCC would instantly become one of the strongest contenders. The black hole bounce hypothesis is not as well researched, but it tells a completely different story. Our universe may have formed inside a black hole in a parent universe. It doesn't have as many mathematical details in its estimates as LQC or CCC, but some models suggest slightly different starting conditions that could explain why big galaxies and black holes showed up so early. BH bounce events might also leave unique gravitational wave signatures that might be picked up by LISA or DECIGO. These events fit easily into a multiverse-like framework in which every black hole creates a new universe. Some theories say that black hole remnants could live on as dark matter, which is another thing that would work in its favor. The future of these two competing ideas depends on what we see. If strong primordial gravity waves are found with a tensor-to-scalar ratio close to what is predicted by inflation, then inflation will not be questioned. But bounce and cyclic theories will become stronger if gravitational waves are not found, even if the detectors are very sensitive. If non-Gaussianities or CMB anomalies that fit with CCC or Eperotic predictions are proven, the talk will change even more. And BH bounce ideas might catch on if strange gravitational wave backgrounds or early signs of dark matter are discovered. Model viability, theoretical consistency, and embedding. It is one thing to come up with an interesting cosmological model. It is quite another to make sure that it makes sense theoretically and can fit into a larger, more established scheme of physics. A lot of ideas about what might have happened before the Big Bang sound interesting, but whether they are possible to prove relies on whether they can be derived from or fit into quantum gravity, string theory, or general relativity, GR, without creating problems. By looking at how different models do under these conditions, we can tell the difference between ideas that are just guesses and ones that have real scientific support. Inflation remains the benchmark for theoretical embedding. While its mechanism is not fully understood, it comfortably fits within quantum field theory and general relativity. Inflation is typically modeled using a scalar field called the inflaton, which slowly rolls down a potential driving exponential expansion. The mathematics is well behaved, and predictions match observed CMB fluctuations almost perfectly. However, inflation has its own theoretical challenges. Many inflationary potentials require fine-tuning to produce the observed spectral index and low levels of non-Gaussianity. Some high-energy versions predict levels of primordial gravitational waves that Planck data has already ruled out. Furthermore, embedding inflation in a quantum gravity framework, such as string theory, has proven difficult. Some versions of string theory favor eternal inflation, which raises paradoxes, including a multiverse with no clear predictive framework. Thus, while inflation is consistent with known physics, it's far from being a fully complete theory. Loop quantum cosmology, LQC, stands out for being firmly rooted in a candidate quantum gravity framework, loop quantum gravity, LQG. LQC doesn't just speculate about a bounce, it derives it mathematically from the discrete quantum geometry of spacetime. In LQC, the classical singularity is replaced by a quantum repulsion that becomes significant at Planck densities, naturally producing a bounce without violating energy conditions. This makes it one of the most internally consistent alternatives to inflation. The challenge, however, is connecting LQC predictions to real-world observations. Its unique features, such as small oscillatory corrections to the CMB spectrum, are subtle and have yet to be confirmed. Additionally, embedding LQC into a full cosmological history, including the formation of large-scale structure and dark energy evolution, is still a work in progress. Eperotic and cyclic cosmologies have their own strengths and weaknesses. The original Eperotic model is embedded in brain cosmology and M-theory, giving it a foundation in higher dimensional physics. In this picture, our universe is a three-dimensional brain moving in a higher dimensional bulk. with the Big Bang caused by brane collisions. This makes it theoretically attractive because it uses the tools of string theory to explain the bounce. However, many versions of the Eperotic model suffer from instability problems. During contraction, small anisotropies can grow uncontrollably, disrupting the smoothness required for a successful bounce. The new Eperotic cosmology resolves this by introducing ghost condensate fields, which are mathematically stable but require fine-tuned scalar potentials that have yet to be derived naturally from M-theory. Embedding the ghost condensate bounce in a complete string-theoretic model remains an open challenge. Conformal Cyclic Cosmology, CCC, is perhaps the most radical in terms of embedding because it works entirely within classical general relativity, but applies a bold new interpretation of its mathematical structure. CCC relies on conformal geometry, which rescales space-time so that the infinite cold future of one universe can be smoothly transformed into the hot, dense beginning of the next. This approach avoids the need for new physics like quantum gravity, but assumes that all massive particles will eventually lose their mass, leaving only massless radiation, a requirement that's plausible but not yet proven. CCC also struggles to fully embed itself in particle physics because it doesn't explain how standard model particles regain mass after the transition between eons. While mathematically elegant, it's not yet fully consistent with what we know about particle behavior. The black hole bounce, BH bounce idea, while intriguing, remains the least developed theoretically. The notion that black holes could spawn new universes fits conceptually within general relativity if singularities are replaced by quantum gravitational effects, but no complete mathematical framework currently describes this process. Some attempts to embed it in LQG suggest that black holes might transition into white holes, leading to new universes, but these are still early theoretical explorations. In string theory, similar ideas appear in discussions of black hole information paradoxes, but no consensus exists. The BH bounce remains more of a philosophical possibility than a fully consistent physical model. Theoretical consistency and embedding help us decide which models are worth giving real thought to. Even though it has problems with fine-tuning, inflation is still the most successful theory based on observations and math. When it comes to quantum gravity consistency, LQC is the best option. On the other hand, Eperotic models show promise if their M-theory embedding can be made stable and natural. In terms of particle physics, the CCC is still semi-classical and speculative, and the BH bounce is still too new to fight. Numerical simulations and current status. Theoretical consistency and embedding help us decide which models are worth giving real thought to. Even though it has problems with fine-tuning, inflation is still the most successful theory based on observations and math. When it comes to quantum gravity consistency, LQC is the best option. On the other hand, Eperotic models show promise if their M-theory embedding can be made stable and natural. In terms of particle physics, the CCC is still semi-classical and speculative, and the BH bounce is still too new to fight. Inflationary models are by far the most developed numerically. Simulations have been used extensively to model the growth of quantum fluctuations, their transformation into classical perturbations, and their imprint on the CMB power spectrum. Modern inflationary codes can reproduce the observed scalar spectral index, NS approximately 0.965, the near Gaussian distribution of fluctuations, and the small amplitude of running. Simulations have also explored different inflationary potentials, ruling out those that predict too much power at large scales or strong primordial gravitational waves inconsistent with Planck data. However, inflationary simulations face challenges in modeling the initial conditions, specifically what set up the inflaton field before inflation began. Since inflation doesn't solve the singularity problem, simulations cannot extend back to time zero, leaving the pre-inflationary phase unknown. Loop quantum cosmology, LQC, has made major strides in numerical simulations over the past decade. Using the discrete equations derived from loop quantum gravity, LQG, researchers have successfully simulated full cosmic bounces. These simulations show that, as the universe contracts to Planck scale densities, a repulsive quantum geometric force halts the collapse and causes a smooth transition into expansion. One of the key achievements of LQC simulations is the reproduction of scale-invariant perturbations similar to those seen in inflation, though with slight oscillatory features at very large scales. Current simulations also confirm that LQC's bounce is non-singular and stable for a wide range of initial conditions. However, LQC still faces challenges in connecting the quantum bounce phase with the classical evolution that follows. There are also open questions about whether LQC can naturally explain large-scale anomalies in the CMB or whether additional mechanisms are needed. Number-based work on eperotic and cyclic cosmologies has also come a long way, especially when it comes to improving the new eperotic cosmology with ghost condensate jumps. Early computer tests showed that the first eperotic situation had anisotropy instabilities, which are small differences in direction that got worse when the system contracted. New models with ghost condensate fields have been tried numerically and show a lot more stability. This proves that a smooth bounce is possible without causing chaos. Simulations also show that these models can make density changes that are almost constant with scale, which is a big win that puts them on par with inflation. However, it is still hard to accurately model the change from contraction to expansion because it takes fine-tuning the interactions between scalar fields. Also, as of now, no full simulation has included multiple successive cycles to show that a truly eternal cyclic world is possible. Conformal Cyclic Cosmology, CEC, is more difficult to simulate because it involves conformal rescaling between eons rather than dynamic bounces. Some numerical work has attempted to identify CCC's unique predictions, such as concentric low-variance rings, Hawking points, in the CMB. Simulations have been run to test whether these rings could arise naturally in standard lambda CDM as random noise, and most independent studies argue they can. Penrose's team, however, claims their own simulations show statistically significant clustering of these rings, consistent with CCC. This debate remains unresolved because simulations of 300 depend heavily on assumptions about how energy transfers between eons, and no widely accepted computational framework exists yet to model this transition from first principles. When it comes to simulations, the black hole bounce, BH bounce theory, is still very new. Some early studies using simplified models of quantum gravity show that black holes' interiors might bounce and change into white holes. However, these studies mostly use one-dimensional or semi-classical models. Modeling Planck-scale quantum gravity effects inside black holes is so hard to do on a computer that it is not yet possible to do full 3D numerical relativity models of these kinds of processes. So, BH bounce is still mostly an idea, and there aren't many quantitative statements that can be tested. The current status of these simulations reflects the state of the field overall. Inflation dominates because its predictions have been extensively simulated and confirmed, while alternatives are still catching up. LQC and eperotic models are making progress, but they need to produce sharper, unique predictions that can be compared directly to CMB and large-scale structure data. CCC and BH bounce remain mostly theoretical, with only limited computational work to support their claims. Numerical astronomy seems to have a bright future ahead of it. New simulations will probably mix quantum gravity effects, scalar field dynamics, and large-scale structure formation in one framework as computers get faster and better algorithms are made. This will make it easier to test the science of the time before the Big Bang. For instance, LQC and eperotic simulations should soon make accurate predictions for non-Gaussianities and gravitational wave spectra. Also, better CCC models might show if Hawking points are actually statistical artifacts or not. Experimental roadmap, CMBB modes, gravitational wave detectors, and all-sky surveys. Cosmology will be shaped by one thing for the next 10 years: data. To stop guessing and find out for sure if the universe had a past before the Big Bang, we need accurate measurements that can tell the difference between different models. A big plan for experiments is already in place, and it includes CMB polarization scans, next-generation gravitational wave detectors, and huge surveys of all the galaxies in the universe. These projects could either prove or disprove inflation, test the bounce and cyclic models, and even look for signs of past cosmic ages. The most anticipated target is the detection of CMBB mode polarization, the swirling pattern in the polarization of the cosmic microwave background caused by primordial gravitational waves. Inflation strongly predicts such waves, with an amplitude measured by the tensor-to-scalar ratio R. If experiments detect B modes with R above roughly 0.01, it would provide strong evidence for inflation and be a major blow to bounce and cyclic models, which predict far weaker or negligible primordial gravitational waves. On the other hand, if no B modes are detected even at sensitivities as low as R, approximately 0.001, it will significantly strengthen loop quantum cosmology, LQC, eperotic and cyclic scenarios, which naturally suppress tensor fluctuations. Several missions are at the forefront of this search. LIGHTBIRD, scheduled for launch by JAXA and NASA, is designed specifically to measure B modes across the entire sky with unprecedented sensitivity. Ground-based observatories like CMBS-4 will complement LIGHTBIRD by focusing on smaller patches of the sky at higher resolution, improving constraints on both tensor modes and non-Gaussianities. If unique non-Gaussian patterns emerge, such as local-type bispectrum features predicted by Eperotic models, it would provide compelling evidence for pre-Big Bang contraction. Gravitational waves are moving beyond the CMB and into a new era. The Laser Interferometer Space Antenna, LISA, a new space detector that will be launched soon, will look for gravitational waves in the millihertz range. This will give us a whole new way to understand the science of the early universe. Inflation predicts a low-frequency gravitational wave background that doesn't change much with size, but bounce cosmologies may predict a blue-tilted spectrum, which means that there is more power at smaller sizes. It is very likely that LISA would prefer bounce cases to standard inflation if it finds such a blue-tilted background. If the black hole bounce, BH bounce theory is right, even more sensitive future missions like DeSigo and the proposed Big Bang Observer could directly find faint signs of a bounce before the Big Bang, or even bursts from black holes turning into white holes. All-sky galaxy surveys are mapping the distribution of matter to test how early universe fluctuations evolved into today's cosmic web. Missions like SPHER-EX, spectrophotometer for the history of the universe, and DESON, dark energy spectroscopic instrument, are critical for measuring baryon acoustic oscillations, BAOs, and the growth of cosmic structures. Standard inflation predicts a specific relationship between the BAO scale and the expansion history, while bounce and cyclic models can introduce slight deviations, especially at very large scales. Euclid, recently launched by the European Space Agency, will provide further precision by mapping billions of galaxies up to 10 billion light-years away, tightening constraints on early expansion and dark energy evolution. These surveys will also help resolve the Hubble constant tension, which may hold indirect clues to pre-Big Bang physics. If the tension persists even with better data, it could imply that early dark energy or exotic scalar fields, possibly remnants from a pre-Big Bang phase, affected the expansion history. SphereX and DESI will help determine whether the early universe deviated from standard lambda CDM predictions. Looking for spectral changes in the CMB is another interesting area of research. Plans for missions like the PIXI, Primordial Inflation Explorer, will look for small changes in the CMB's perfect blackbody spectrum. Some bounce models predict small amounts of energy being injected that wouldn't show up in a standard inflationary theory of the universe. PIXI could also put more limits on isocurvature changes, which are not allowed during inflation, but are in some cyclic and ekpherotic situations. With better CMB maps, it might be possible to directly test the forecasts of the CCC. If Hawking points or concentric low-variance rings are real, future efforts with better noise reduction could either prove them or definitively negate them. If it turns out to be true, it would be one of the most important finds in the history of cosmology, proof that our universe got information from a long time ago. Here is the most organized plan ever made for experiments to find out if the Big Bang really was the beginning. Each mission is aimed at a different part of the puzzle. When all of them work together, they could either prove the standard model of inflation or reveal new physics that goes beyond the point we call the beginning of the universe's past. Potential future breakthroughs: Hawking points, primordial waves, and pre-Big Bang dark matter signatures. The coming decades promise to be a golden era for cosmology, with the potential for discoveries that could rewrite our understanding of the universe's origin. Among the most anticipated breakthroughs are the detection of Hawking points from a previous eon, the confirmation or lack of primordial gravitational waves, and possible evidence of pre-Big Bang dark matter signatures. Any one of these findings would shake the foundations of the standard cosmological model. Combined, they could provide overwhelming proof that the Big Bang was not the ultimate beginning. Consistent proof of Hawking points, which are circular hotspots in the cosmic microwave background, CMB, that were predicted by Conformal Cyclic cosmology, is one of the most exciting options. Hawking radiation caused giant black holes to disappear in the far future of the last eon, according to the CCC. The last bursts of energy from these black holes would have left behind faint marks that can be seen in the CMB today, as low-variance circular areas a few degrees across. There have been claims by Roger Penrose and his team that they have found dozens of these spots in WMAP and Planck data. However, these claims are still debated because different statistical studies have come to different conclusions. If future missions like CMBS-4 or LIGHTBIRD can strongly support these Hawking points statistically, it would be clear proof that our universe got information from a previous time period. This would be a discovery as groundbreaking as finding the CMB in the first place. Equally important is the search for primordial gravitational waves, which could finally settle the debate between inflationary and pre-Big Bang models. Inflation predicts a nearly scale-invariant background of gravitational waves, with an amplitude expressed by the tensor-to-scalar ratio R-bounce, and Eperotic models, in contrast, predict either extremely suppressed tensor modes or a blue-tilted spectrum, where gravitational waves are stronger at smaller scales. Missions such as LIGHTBIRD and CMBS-4 are designed to measure B-mode polarization in the CMB with unprecedented sensitivity, potentially reaching R values as low as 0.001. A detection consistent with inflation would strongly favor the standard Big Bang model. Conversely, a complete lack of B-modes at this sensitivity, or the detection of a distinctly blue-tilted gravitational wave spectrum by LISA or DeSigo, would lend strong support to bounce scenarios. Gravitational wave astronomy could also give us shocks we didn't expect. If black hole bounce, BH bounce models are right, some gravitational waves could come from things happening inside black holes, like when they turn into white holes or when new worlds are created. These events could cause bursts that are different from normal black hole mergers. Finding these kinds of signs would be a roundabout way to show that black holes are not dead ends, but rather portals to new stages in the history of the universe. Another potentially groundbreaking avenue involves pre-Big Bang dark matter signatures. Some theories, such as those by Carlo Rovelli and Francesco Vidotto, suggest that remnants of black holes from a previous cosmic cycle, stable Planck mass relics, could make up dark matter today. If so, these ancient objects are literal fossils from a pre-Big Bang universe. Detecting them directly would be nearly impossible due to their tiny size and weak interactions, but microlensing surveys and gravitational wave detections of unusual low-mass mergers might provide indirect clues. Some ideas say that some dark matter particles, like ultralight scalar fields, were made before inflation or a bounce and carry information from that earlier phase. It's possible that these particles will leave small changes in the CMB's small-scale power spectrum or in the way galaxies are spread out. More detailed maps of the cosmic web are being made by studies like SPHEREX, Euclid, and DESY. Researchers will look for these small problems that inflation can't easily explain. Future breakthroughs may also come from spectral distortions in the CMB. The proposed PIXRE mission could detect tiny deviations from the CMB's perfect blackbody spectrum, Some pre-Big Bang scenarios predict unique energy injection signatures, such as those from quantum gravity effects during a bounce or from exotic particle production in a contracting phase. Detecting such distortions would be another major step toward proving that the Big Bang was not the first moment of time. All these discoveries will be pieced together to form a coherent picture. No single observation will settle the question of what came before the Big Bang, but a combination of Hawking points, gravitational wave spectra, dark matter relics, and CMB anomalies could make a compelling case. For example, a lack of inflationary gravitational waves combined with confirmed Hawking points and evidence of pre-Big Bang dark matter would strongly favor CC or cyclic models. Conversely, a clear detection of inflationary B modes would cement the standard Big Bang narrative, though it would still leave the singularity problem unsolved. Even though cosmology has come a long way and there are many experiments coming up, some of the most important questions about how the world came to be are still unanswered. These questions are not small ones. They are big holes in our knowledge that keep the conversation about the time before the Big Bang going. It's still not clear whether the universe started with inflation, a quantum bounce, or something else. These unanswered questions are the key to figuring out what happened before the Big Bang. The first major unknown is the trigger, what started inflation or what caused a bounce if one occurred. Inflation requires a scalar field, the inflaton, to roll down a potential, but we still don't know where that field came from or why it had the right properties to drive exponential expansion. Its potential must be finely tuned to match observations, raising questions about whether inflation was inevitable or just one outcome among many possible initial conditions. Bounce models face a similar mystery. What determined the transition from contraction to expansion? In loop quantum cosmology, LQC, quantum geometry forces naturally create a bounce at Planck densities, but why the universe reached such a state in the first place is still unclear. In eperotic and cyclic models, the timing of brane collisions or ghost condensate transitions remains unexplained, leaving the ultimate cause of the bounce an open question. Closely tied to this is the mystery of scalar fields. Many pre-Big Bang models rely on them, from the inflaton in inflationary theory to the fields that drive contraction and bounces in eperotic cosmology. But what are these fields physically? Are they related to known particles, or do they belong to an entirely hidden sector of physics? If they exist, they might also be linked to dark energy or dark matter, potentially acting as a unifying force across cosmic epochs. Yet no experiment has directly detected any such field, and we don't know if they are fundamental or emergent phenomena. The science of branes in models with more dimensions is another big puzzle. Some forms of string cosmology and the eperotic scenario depend on the idea that the universe is made up of a three-dimensional brane surrounded by a higher dimensional bulk. This picture shows that brane crashes caused the Big Bang. In M-theory, brane interactions are potentially possible, but we still don't fully understand how they work, how stable they are, or how they cause the patterns we see in the cosmic microwave background. Since there isn't a full quantum theory of brane dynamics yet, these possibilities are still just guesses. Then there's dark energy, which is still a mystery. Is it really always the same, or does it change over time? The usual KCD-M model sees it as a constant in the universe, but if dark energy changes, it might be what controls the cycles of the universe. The universe might be able to grow, contract, and bounce back and forth many times, with the Big Bang being just one of many phases. Soon, observations from Desai, Euclid, and Sphere may show whether dark energy has always been the same or if it changes over time. This could change how we think about the universe's long-term future and its history before the Big Bang. The amazing thing about astronomy is that every answer brings up 1,000 more questions. We're getting closer than ever to finding out if the universe started with inflation, bounced from another universe, or still holds secrets from a very long time ago. The next 10 years could finally show what happened before the Big Bang, or they could show that time doesn't really start. If these crazy ideas are interesting to you, stay with us here on Beyond Horizons. Please like, subscribe, and share your thoughts in the comments. The discussion about the real start of the universe has just started.